We'll see that. Yeah, continue. Can people see that?
Yep.
All right, how are we doing for the attendance? Are we close to what we want? 37.
Yeah, we're close enough.
All right, good morning, people. How are you doing? Did you enjoy watching videos last night? It's not really Netflix and chill, but it's Heliophysics summer school and chill. So let me just start off by giving you an idea of what this is supposed to be. When we started this format, not the online format, but just basically the format we have now, we thought there should be some introductory materials for some of the topics that could be approached by anyone. So this is non-specialist stuff. And we framed a couple of questions, which we thought anyone in heliophysics should be able to come up with a reasonable answer to these questions. So the first question was, why is it that the sun and planets have magnetic fields? And I find myself answering this question to members of the general public all the time, more often the Earth, but they're also surprised to learn that the sun has a magnetic field. Now, you're all much further along than that, but we want to make sure that everyone in heliophysics, even if you study the ionosphere, and so magnetic fields are a much smaller part of your life, are able to think along these lines. So that's where these courses came from, these lectures. And along that line, I study only solar flares, but I, was going to put my money where my mouth is and say, if I think students should be able to come up with halfway decent answers to this, I should be able to do the same. And so I give the lectures on all these topics using the heliophysics textbooks or the principles of heliophysics as we now have it. So the answer, just as a spoiler alert, is the reason they have these magnetic fields is that they all have something called a dynamo. And here are pictures of some of the dynamos we all know and love, sort of a rendering of the sun's magnetic field. You see everything here is given some idea of a little magnetic field, including a beautiful picture of Saturn and then a close-up of Jupiter's aurora, which gives you an idea that, yes, they have magnetic fields as well. So there's the answer. And the sort of one of the lecturers coming up will go into greater detail on this, but in her earlier lectures she gave, she basically said, yeah, anything that has 3 ingredients here will generate its own magnetic field. And the first is having an electrically conducting fluid, which for stars is plasma, for terrestrial planets is liquid iron, gas giants have metallic hydrogen, and some ice giants have ionized water. This fluid must have complicated motions. So really we need turbulent flows. And often we do need rotation to break mirror symmetry if we want a large scale magnetic field instead of just a turbulent mess. So rotation is kind of not a necessity, but it certainly makes things a lot more recognizable. And finally, we need these motions to be vigorous enough. And we're going to get into just some of the details of what that means. It all comes down to the magnetic Reynolds number, which is the velocity and the size of the object and the conductivity of this electrically conducting fluid. So you can see, even if your conductor is not so great, so this conductivity factor is not so high, you can make up for it with, say, size. You're dealing with a big planet. It's got size on its side, and a lower conductivity may actually not be a killer. And here is an example I used in the lecture, and I went through it in great detail. I'm not going to do that here. A toy we call a homopolar dynamo, and it just shows you how kind of ingredients like this all work. Instead of a conducting fluid, it's just a 2-part gizmo built out of metal. It's not a single object built out of metal. That wouldn't do. You need differential motion. So here you just have a rotation of a disk relative to a stationary wire. And it does lack mirror symmetry. And as I explained in the lecture, if there's a magnetic field that goes up through it, what you get out of it is, oops, I thought I had, those are all the calculations. You basically drive a current from the axis to the edge of the disk, and then it goes back through the wire, and that's just oriented in such a way that it will amplify the magnetic field. So then that will drive a stronger current, and that will continue to amplify the magnetic field. And I went through what the voltage is across the disk. And from axial to rim, the voltage drop is proportional to the flux going through the disk and the rotation rate. And then I just basically analyzed it like it were a circuit. We have IR is equal to the EMF, and there's this motional EMF, which is generating it. And then there's a back reaction, a back EMF from its self-inductance. And then I rewrote this all, and you get basically a differential equation for current, which involves the rotation, which is the generator, is out here in the orange box, and then the dissipation is the resistance. Okay, and that basically goes into a growth rate gamma. So the current will grow or decay exponentially. Okay, so this is one of these instabilities in nature. It's a positive feedback loop. And so you're just going to get exponential growth or decay. For growth, you need this full factor to be greater than 0, which means you need the rotation rate to exceed this expression here. And you rewrite it and you find out that that's really the same as saying if these units, we need a magnetic Reynolds number. Magnetic Reynolds number has a conductivity in the denominator. So we need this as in the numerator. So we need the magnetic Reynolds number to be greater than 2 pi. So again, we see conductivity, size, and velocity. The product of those three things just has to be bigger than this value, and then you'll get exponential growth. Okay, so that just sort of gives you an idea that that can happen in a special case. Here is the system that we actually work with, not a spinning disk, but a fluid, and it satisfies these 4 equations, which are the equations of magnetohydrodynamics: mass continuity, a momentum equation, an energy equation, and what we call the induction equation, which is really Faraday's law and Ohm's law put together. The situation we often consider, we have a force from the magnetic field and we have some heating from the magnetic field. But if the magnetic field is weak enough, we can just discard those. And then we have 3 equations, which are the classic equations for fluid dynamics. Okay, mass, momentum, and energy with no magnetic field around. So you can just work out what the flow is doing. And then after you've done that, you just solve this linear equation for B. Okay, so what you get are linear equations for B once you know the velocity. And here's the next trick I used, which is to rewrite some of these, use a vector identity to rewrite some of these terms and basically show that this is the time derivative of B following the fluid is given by B times a matrix, and the matrix involves this velocity. And what you need is for this matrix to have a positive eigenvalue, and you'll get that exponential growth. Okay, the eigenvalue is sometimes called the Lyapunov exponent. So as long as that value is positive, you'll get exponential growth. Well, if it's positive and bigger than the dissipation term over there, okay, which is really brings us right back to the magnetic Reynolds number. So we just need the magnetic Reynolds number to be bigger than, in this case, kind of 1-ish, right? Depending on how how this velocity and length are related to this eigenvalue. You do need the eigenvalue of this matrix to be positive. And what kinds of turbulent flow, what kind of flows have positive Lyapunov exponents? The simple answer is turbulence. If the flow is going to take little bits of ink, say, and stretch it, basically mix your cream into your coffee, if it's capable of doing that, it's got a positive lambda. So any turbulence will do. The conditions for turbulence is that you need you need a velocity to be big enough to overcome viscosity. That is a Reynolds number, not the magnetic Reynolds number, of much, much bigger than 1. Any flow that has a Reynolds number much, much bigger than 1 will spontaneously just become turbulent. So that's what you really need in a fluid conducting fluid, a fluid to get turbulence. And if that fluid is a conducting fluid, it will give you the extension of magnetic fields that you're looking for. And in order for the rotation to matter, you also need this characteristic, which has a velocity in the numerator and the rotation rate in the denominator. The Rossby number, sort of defined upside down in my opinion, it has to be much, much less than 1. And here are some examples of those values for the sun and the earth. And we can see in all cases, it works. We have a magnetic Reynolds number, which is not so huge for the earth and is truly huge for the sun, etc. The Rossby number for the sun, we'll get back to this, is kind of not as small as you might want. And we'll get back to that as well. So that's really how our 3 ingredients work. And this is how it works for the sun. Our conducting fluid is a hydrogen helium plasma, right? You couldn't ask for a better conductor than a plasma. All the electrons are free of those pesky ions. So you have free moving electrons. It's even better than in a piece of copper where the electrons have to be in some kind of conduction band and you have Fermi surfaces, blah, blah, blah. A plasma is much simpler than that. It's just the electrons get to go wherever the heck they want. The convection zone, which is the outer 1/3 of the sun, does actually have the second characteristic. It has turbulence. It is trying to move the heat from the inside of the sun to the outside, and that turbulence is what's going to do all of the motion that will move our magnetic, that'll do our magnetic stretching. Okay, and it's a relatively good conductor. And so according to those ingredients, we should have a magnetic field on the sun. And as almost all of you, if not all of you know, it does have a magnetic field. The early indications were in the sunspots that people observed, way back into history. And now that we can make measurements of the magnetic field, we see that these sunspots come in pairs, or the groups come in pairs, positive and negative, leading and following. And those show, positive and negative basically shows that the magnetic field is popping out of the sun. Sorry. Okay. I think that was not really intended as a comment. So we have magnetic field. And in the sun, that magnetic field goes mostly around, parallel to the equator, around lines of constant latitude. That is known in the business as toroidal field. It's mostly an east-west field, and it seems to be bundled into fibers. Okay, so we have the ingredients we thought we needed, and indeed, it seems like those ingredients, at least in the case of the sun, do generate a magnetic field. On the first day, I brought this dynamo generation as an example of an oscillator. And I just argued that the sunspots themselves are the toroidal field. And here are records of some of the toroidal fields from, beginning of the end of the 19th century. And you see it oscillates. That is the well-known sunspot cycle. When you measure the north-south component, the poloidal field, it also oscillates. And you can see from this diagram, sort of, that it is 90 degrees out of phase with the toroidal field, right? Here we have the poloidal field in the northern hemisphere and the southern hemisphere. And those are 180 degrees out of phase with each other, as you'd expect for a poloidal field. But they peak when the sunspot number is at its lowest, okay? When they peak, you're at solar minimum. So this really does sound like an oscillator. You have, just like in a simple harmonic oscillator, you had an oscillation between kinetic energy and potential energy trading back and forth. Here it looks like you have poloidal field becoming toroidal field becoming poloidal field. That is the nature of the oscillation. Or they're 90 degrees out of phase the way in an LC circuit, the charge or the voltage on the capacitor is 90 degrees out of phase with the current in the inductor, right? Very similar patterns here. So this is just a self-sustaining oscillation. And I want to go into a little more depth about how this works, because this is something that sort of looms large when we talk about long-scale variability in the heliosphere. So the first thing I want to do is look at one of the conversions, poloidal field becoming toroidal field, okay? And that is thought to occur through differential rotation. If the sun were just a rigid rotator, we don't think this would happen. But the way the sun rotates, I don't have a picture here, but you're probably familiar. The equator rotates faster than the poles. And so I believe one of the exercises you may have been assigned, but if you weren't, it's not super difficult. We want to say how long does it take before the poles, which are rotating, the equator, which is rotating fast, rotates one complete turn more than the poles? Or put it another way, if I co-rotate with a pole of the sun, how long before I see the equator do one rotation? And the period for equatorial rotation is, I just put in a rough number, 25 days. For the poles, another rough number, 35 days. So if I convert those to frequencies, right, I just take the reciprocal, what you're really looking for is what's the difference of those frequencies, right? If I lock myself to one frequency, then what do I observe is the other oscillation at a different frequency. So this is not oscillation, I should say, this is rotation. And the difference between those two, you can even do this in your head, it's 0.011. Taking the reciprocal, you might not be able to do in your head, but it's 87 days. So in this example, even though the sun rotates every, let's say, take an average 30 days, it really takes almost 90 before the equator has rotated one complete turn farther than the poles. And we can just check that. If I look at the number of rotations the equator has undergone, that's 87 over 25, 3.5, and the poles, 87 over 35 is 2.5. So from our reference frame, both of them have rotated, but the equator has rotated one complete turn more. Okay, so write this number down, because what I want you to do, I think we are ready to break up into groups. I want you to look at activity 47 if you have not done it already. Or if you have, just go into your groups here and try to come up with an answer to the following question. If the sun's polar field poloidal field starts out at 5 Gauss, so just take that as sort of the north-south field, how long would it take to stretch that into 100,000 Gauss toroidal field? Now, this is not going to use the dynamo equations. This is going to use this cartoon or this cartoon along the bottom. And the book gives you a hint that you're supposed to look at compound interest. That's a cute way of phrasing it. I think we're all comfortable with exponentials. So the trick here is that what this process is doing is actually making the toroidal field grow exponentially. And its starting value is something like the poloidal field, 5 Gauss. So given what we know about the differential rotation, well, I just worked out, break up into your groups and come up with a number. How many minutes, days, hours, years is it going to take a 5 Gauss magnetic field and stretch it using this stretch, twist, fold type mechanism, which is amplifying toroidal field to amplify it up to 10,000, 100,000 Gauss. Okay, is everyone clear on your exercise? Let's see, I'm going to stop sharing at this moment.
Dana,
let's see.
how long do you want? It's 24 minutes.
How about we give everyone 10 minutes? So
10
we'll be back at 35 minutes past the hour.
Okay.
That should be enough time to work it out. And so just try to use an exponential when you're doing this calculation. Oh, and there was all sorts of.
Okay, breakout rooms have been closed, so everyone should be back within the next 50 seconds.
Okay.
5 seconds.
5 seconds. Okay, good. Okay. 3 p.m. tomorrow.
Yep,
All right.
everybody's back.
Looks like everyone's back. Okay, folks. I think I saw some groups really going to town with this. Others may not have gotten everything. This is a cartoon example, but it really will show us something important about the dynamo we're dealing with here. And it's how the differential rotation will turn poloidal field into toroidal field and how long that could take. Does someone from any group want to just volunteer and give us a quick explanation of how you got an answer and what answer then you got? I saw a couple right on getting the exact answer, so someone must want to volunteer.
I'd be happy to speak up. So we just went by, first of all, determining the number of rotations it would need in order for the 5 Gauss magnetic field to increase to 10 to the 5th. Did that by setting 5 times 2 to be x equal 10 to the 5th, where x is the number of rotations. And so x is 14.3 in that case, 14.2829. And then multiplying by the number of days it takes for the equator to lap the poles. 87, we got around 1,244, which is roughly 3.4 years.
Okay.
I think that's right.
Anyone want to add or modify or fill in some of the steps there? Or any questions? I think I got 3.4 years. Yeah, I think I got a number that was maybe 5 days off yours. So yeah, the key observation here is that in this cartoon, you go from 1 loop to 2 in the whole cycle. And then you're going to start with 2 and get 4. You're going to start do 4 and then get 8, etc. So it's going to double every time you can do a stretch fold twist. And the next observation is that doesn't have to do with the rotation of the sun, right? I mean, if it were a rigid object, you just stay at 2, you stay at 1 loop all the time. It really has to do with the fact that the equator is going a little bit faster than the poles, and after 87 days, it's done a complete rotation. And that's what this bottom cartoon is supposed to show you. This is after many, many rotations of the equator. You can see the equator is rotated many, many times more than the poles. All right, so as crude as it is, this is one of the key ingredients in the dynamo. And we can see from this estimate, it's going to take to really build up the field we see some number of years. And if you think this is crude, maybe it's twice as many years. So that already tells you why the solar cycle is roughly as big as it is. A half an oscillation or a quarter oscillation, if you want to call this the first half of the first half, is 3 years long. Okay, so that fills in the poloidal, converting poloidal to toroidal field. The way back is more complicated. And there are several answers to that. Professor Bhattacharjee will later on today describe in great detail something called the alpha effect. This is a result of mean field dynamo theory. And that does the trick of converting toroidal to poloidal fields. What the principles of heliophysics does in chapter 4, some of the sections, is to go through something called the Babcock-Leighton dynamo, which may or may not be related to the alpha effect, but most people think of it as distinct because it really looks at the surface magnetic field. And what it observes is that when these sunspots emerge, they're mostly poloidal, they're mostly toroidal. They go east-west or west-east, but they are tilted when they emerge. And that's known as Joy's law. There's a tilt of these angles, and that tilt gives us a little bit of a poloidal field. So that's converting the toroidal field to the poloidal field. And the tilt is really due to the Coriolis effect. So it really is involving rotation once more. To look at this, I want to just use a little tool that solar physicists are very fond of. Actually, I think geophysicists are too. It's called a synoptic plot. And instead of the image, the round image of the sun here, what you do is look at the center and unroll it. And there are some cool movies of them. I don't have one here, but you unroll it so that you see the longitude from 0 to 360 as the x-axis and the latitude or the sign of the latitude as the y-axis. And that gives us a view of the full sun. Now, it takes a while to produce that, but anyway, you get the picture. And so here is the basic idea. When these active regions emerge, and here we see an image where we see the active regions slightly tilted. And now I have a smoothed out version of this synoptic plot, because this is actually a calculation where I plop an active region in at exactly the observed size and the observed tilt and the observed location. And you can see that because it has a tilt, there's a downward poloidal field. The other thing you see from this is at the moment, there is a positive region around the North Pole and a negative region about the South Pole. So in a sense, the poloidal field that's being generated is opposite to that. That is, the dipole moment is pointed northward. And you can see if I average out all the fields. So now I do one more step. I take this synoptic plot and I average across lines of latitude or a sign of latitude. And I have this black curve. And you can see the big positive bulge in the North Pole and the big negative bulge in the South Pole. And if I look at the average, I get this dash dotted line. That is the dipole moment of the sun. That is what we've been using as the poloidal field. And that is at the moment negative, right? It points, it points. It has negative in the negative in the southern hemisphere, right? But the sunspots are going to override that. So here's a movie of the same thing, and you'll see that nice little plot on the right. You'll see this, and this is one I made by just taking a list of all the active regions that emerged for I think up until Carrington rotation. But here's what the movie looks like. And this involves two effects really going on simultaneously to show how this field evolves. It involves the emergence of the sunspots in these tilted regions, and then a slow diffusion of the sunspots and a northward, or sorry, equatorward motion, a poleward motion by what's known as meridional circulation. So a flow. Oops, let's see, Here's a version of that all stretched out. So you can see what's just happened. The dipole moment, as we said, started out, and for a while, the dipole moment was positive. And then these emergences happened and it drove the dipole moment negative. So we started out with positive field on the North Pole and negative field on the South Pole. Then a whole bunch of active regions emerged, and that forced the poles to reverse sign. Okay, so the dipole moment went from positive to negative, and you can see up above the sunspot number. These are not quite, but almost 90 degrees out of phase. You can see where the sunspots peak is when the slope of the dipole moment is getting large, maximum, and then it goes down. So this is what's known as a flex transport dynamo. It sort of does the field reversal, the toroidal field turning into poloidal field by emergence of active regions and then generation through diffusion and advection. Okay, and here's the history for well, at least how long is this? 35 years, 3 cycles. The sunspot number plotted along the bottom. Here is the dipole moment of the sun, slightly different units here. And that is going from positive to negative, back to positive, back to negative. And in the green, that is just the Z component of the dipole moment. In the green, I'm actually showing the magnitude of the dipole moment vector, okay? And you'll see the magnitude of that vector never disappears. So what would you say if I told you a vector has 0 z component, as it did on the 24th of January 2000? The z component of the vector is 0, but the vector itself has a finite length. What can you tell me about that? How's that happen? How's that work? A vector has 0 z component, but it doesn't have 0 length.
Dana, there's at least one sideways pointing thumb in the.
Oh, good, yes. So that's exactly right. So the dipole moment becomes weaker, but it does not disappear. It just points. At that point, it is horizontal. It is pointed up. It's within the ecliptic. It's sideways, as you said. It's not north-south, and then it flips around. So what you really want to think about is that the sun's magnetic field, actually, the dipole moment flips from positive to negative, but doesn't vanish. Okay, and it does get a little bit weaker. It's surprising that it's not that much weaker. All right, let's see. So let's finish up here. I will leave you with this, and then we can pick it up after, because I think, Nick, am I, oh, maybe not. I think we didn't start at 9, so how much longer should I go before we break? Maybe, can I go another 5 minutes?
Sure.
All right. So I think some of you worked on activity 51. That is where we think about the process that was going on here is both a diffusion, as if this black and this white stuff were just ink and it's diffusing. And then there's also a flow, as I said, up to the poles from the equator. That's meridional circulation. That is pretty slow. That is 10 meters per second. The sun is a big place. 10 meters per second is 20 miles per hour. If you drive 20 miles per hour on any road in Montana, you will have people passing you all the time. So this is slow. But the diffusion is pretty fast. It's 250 kilometers squared per second. Did anyone, Nick, did anyone do this? This was assigned to some of the groups, right? This example, this exercise?
I believe so.
Okay. If anyone has an answer they want to share, could you just shout it out? How long would it take to, the characteristic timescale defined this way, for the flux to diffuse over the entire solar surface? So basically to disappear after using this diffusion coefficient.
Or you can put it in chat.
Or put it in chat, and Nick will read it off of chat. Anyone? The only trick here is recognizing that D and eta are the same thing. And this is a generic diffusion coefficient. This is just basically for resistivity. No. So LT here I put at a solar surface. That's really the size you're going to need to just disperse it over. So I get 65 years. 65 years. Now, even going as slow as 10 meters per second is on a place as big as the sun, it will take you only 2.5 years to drive from the equator to the poles, basically. So it is the circulation that is much more effective at reversing the field than the diffusion is. Okay, that's really the key driver here, at least in this kind of dynamo, is the motion that takes stuff, at least on the surface, from the equator to the poles, the meridional circulation. And that is sort of how we close the cycle. Let's see, I thought I had a reference back. I'll just go back and show you this cartoon, not the cartoons. So essentially that's, after 2 or so years, you've basically turned the toroidal field back into poloidal field and you're ready to do the oscillation again. Okay. And the other thing you might notice is in that time, you just reverse the field. So you have a full oscillation is actually 22 years. Okay.
Hey, Dana.
Yeah.
So there was actually a response that I missed into your last thing, but there's also a question in chat talking about the flipping of the dipole.
Right.
Is this an effect that occurs every solar cycle?
Yes, this is an effect. So here is what you'd call the solar cycle is what you see on the bottom. That's the sunspots. So there was a maximum in the solar cycle at 1980, a maximum around 1990, and a maximum around 2001 or so. That's the maximum in the sunspots. If you look at the poloidal magnetic field, that is the dipole moment, and just the BZ component, the Z component of the dipole moment, that crossed zero in April of 1980. So really, has a node where the toroidal field has an antinode, and then it flips. So a full period is from 1980 to 2000, 20 years in this case. That's a full period of the oscillation of the sine wave here. And what you're seeing only in the sunspots is only the amplitude of that. So it appears to be more like a 10 or 11 year cycle, but it's really a 22-year cycle. Is that the question that was being asked?
I believe so, but Kenneth can chime in and see if that was helpful.
Yes, thank you.
Okay. So this just emphasizes that, we've seen this cycle persisting. Actually, it takes quite a bit of care to take older records and turn them into sunspot numbers. So you can see it's not done perfectly here, but this is the long-term variability in the sunspot number. We didn't have magnetic field measurements, so I can't really tell you the poloidal field, but you can just assume it's 90 degrees out of phase with this. And you can see the amplitude it's not a perfect oscillator. And we'll discuss a little bit more what that means, but it is pretty darn cyclic, right? It is oscillating a full period every 22 or so years, going back at least into 1600. And we could discuss, but I know you'll get more discussion of much longer cycle variations. So I think now I'll let us break. Is it for 20 minutes, Nick? Are we going to break?
This one's just a 10-minute break.
Okay. We're coming back in 10 minutes. So at 5 past the hour?
That sounds good to me.
But then is it then office hours, or the office hours come after the second?
After the second.
Okay, got it. So let's just break for 10 minutes. And we will be back at 5 minutes past the hour. All right. Do we think we should start up again? It's 5 past.
Yeah, why don't everybody turn on their cameras just to let us, or everybody who can turn on their cameras just to let us know that you're back. And so we're back up to 35, which is roughly where we were at earlier. So, or you can give us a nice clap as a signal that you're back. That's great. Thank you, Sichi. Yeah. Okay. Yeah. It looks like we can start back up.
Okay. Good.
And I will keep an eye on chat since Amitava.
Okay. Thanks. Yeah.
Had to drop off.
Welcome back. So we sort of illustrated for a star the way that a dynamo works, sort of an oscillator, which requires conducting fluid with complex motions that are strong enough to give us a high magnetic Reynolds number. And that will sort of take us to a dynamo and a star. And the next thing I want to do is just look at some other stars. And we have different types of stars based almost entirely on their mass. So a very large star is a B star. Slightly larger is an O star. The sun is a medium-sized star, and an M star is very small. Here, they've shown just the regions of that star according to models that are convective, where we have this ingredients that we're going to need for our dynamo. And you'll see the sun has its outer shell. The M is entirely convective, so it has all of the ingredients. A B star is convective on the inside. So if it generates a magnetic field, that's going to be all on the inside, and it's not going to look very much like the solar dynamo we're used to. If you take a simple model of the the size of stars across this is a Hertz-Spring-Russell diagram, and the bottom axis could be considered temperature. Often it's color, but they're the same thing. And so we have the heaviest stars are the hottest surface temperature, and the coolest and the smaller stars are the coolest surface temperature. If you plot the radius of the star versus surface temperature, it goes from here. I'm just showing F stars. I haven't gone out to the O, B, and A stars. 8,000 Kelvin all the way down to 4,000 Kelvin. And if you figure out what the convection zone portion of that star is, it's actually starts out at 0 somewhere in the F star range. So to have a convective envelope, you really need to be small enough, or the surface temperature needs to be cool enough, but it's really that you're small enough that you drive convection. And so that means there are a bunch of stars that really don't have the ingredients we're looking for. And indeed, if you look at, this is an older version of the Hertz-Spring-Russell diagram, the active stars, the ones that are in this hashed region, are F stars and up, F0 and up. These are stars that are actually observed to be magnetically active. So this is really where we're seeing evidence of that picture, that dynamos require these ingredients. And if you're an A star, you just don't have those ingredients, at least not at the surface. So that is the picture of how this works. The Principles of Heliophysics talks about different non-dimensional numbers that are used to characterize this. And I think for you, some of the activities that you did, one of the activities you did is this activity number 50. And it's to show that the Rossby number here is actually related to the magnetic Reynolds number, and then this other C sub omega. And I'll just go through it. And indeed, what you can do is plug in the definitions they give you for magnetic Reynolds number and turbulence diffusivity. Now, the the magnetic Reynolds number, first, we don't have to do that. You just plug in these definitions, and you get this in terms of the turbulent diffusivity over the velocity. That should be velocity turbulent. And if you recognize that that's the length scale turbulent, you get the answer they're looking for. That is the Rossby number. More importantly, what they give you as an equation is something known as the dynamo number. And that is a product of these two dynamo numbers, something that's involved with the toroidal to poloidal field conversion, C sub alpha, and then the differential rotation, C sub omega. The product of those two gives us a dynamo number D. Okay, and when you put it all together, you have this alpha turbulent, omega turbulent, the radius of the star cubed, convection zone, turbulence diffusivity. If you plug in the definition of turbulent diffusivity and the definition of alpha, I did not put in the factor of 1/3 or the minus sign. This is twiddly math. Really goes as omega times R. Okay. In the end, you get the dynamo number goes as this turbulent frequency omega tau squared times the convective turnover time tau sub c squared. That tells us that the dynamo number, this is actually also the Rossby number. This is the thing that I told you was one of the characteristics. It tells you how important rotation is to your star. That is to say, I always like to illustrate the importance of the Rossby number by pointing out a fallacy that some civilians will have, and that is that the toilets in the southern hemisphere flush going the opposite sense. And that's because the rotation of the Earth is opposite relative to your vertical. And the key is the rotation of the Earth something that your toilet is aware of? And that has to do with how long it takes your toilet to flush divided by how long the Earth takes to rotate. That is what this Rossby number is. And if your toilet takes more than 24 hours to flush, you probably should be calling a plumber. So a normal toilet, which will flush in 20 or 30 seconds, is not even aware it's on a rotating Earth. So that is not a, there are explanations for it if you observe it, but it's not the Coriolis force that's doing it. The Rossby number is out there to tell you when it matters. So a very small Rossby number basically means the rotation is dominating the motions. And that is more true of, say, a hurricane, which takes days for the fluid elements to go completely around the hurricane. And the Earth only takes 1 day to rotate. So the Rossby number for a hurricane is very small, telling you that the rotation of the Earth matters. So what's really key here is that somehow the dynamo number and the Rossby number are intimately related. And the dynamo number is this thing that's going to tell us if we get a dynamo. And the Rossby number just tells us how the star is rotating and how the convection is working. And this was recognized quite a while ago. So one of the ways they do the Rossby number is a theoretical calculation of the convection zone, gives us tau sub c, and then observing the rotation of the star. If there's something that can tell you how fast this star is rotating, and for that you can look at spectral lines, you can look at variations in its brightness, that will tell you a rotation rate for that star. If you take the ratio of those two, that's the Rossby number. So here's the log of the Rossby number for a bunch of stars. And so remember, the Rossby number increases, the dynamo number decreases. So higher dynamo numbers, stronger dynamos are to the left. And then what they plot on the abscissa is the log of something that is basically a proxy for the magnetic field. I can't go into this. It has to do with observing the calcium H and K lines. But you can see in this curve is that the dynamo number increases, the activity, the magnetic field you observe increases as well. So the Rossby number decreases, the magnetic activity increases, yeah. And I should also point out that the rotation, this is brought up in a later chapter. I'm not sure we assigned this, but it is relevant to one of the kinds of variation that Nick did point out. The stars are born, they tend to rotate fast, and then they spin down over time. And this is a typical what's known as Skumanich's law. The rotation rate scales as the inverse square root of time. So the magnetic activity of a star will decrease over time. Okay, and so these are the young stars out here, magnetically active, rotating fairly rapidly, and these open circles are the older stars. And then again, here's another way of plotting color versus activity, magnetic activity. So we see some real evidence of this. Here's another plot with a lot more data points, 824 stars. And here what we're plotting, this is much more familiar to a solar physicist. It's just the X-ray luminosity. How bright is this star in X-rays divided to by how bright it is in all wavelengths, bolometric luminosity. And you'll see the X-rays never account for, are well under 1% of all the brightness, maybe 0.1%, but that's not the world we live in, right? Our sun is 1 part in a million of the X-rays. The X-ray brightness is 1/1,000,000th of the overall brightness. So in order to get a much stronger dynamo, you need much faster rotation. That's basically the story. The Rossby number you have must be much, much lower than the sun's is. In this case, this puts the sun's at 2. It really depends on how you define this convection, the convection zone eddy turnover time. Another way of making the Rossby number very, very small would be to turn that up, right? So if these eddies were turning over very, very slowly, here they're talking about eddies that are turning over once per month. So that's going to give you a very large Rossby number for the sun. So the dynamo number is increasing to the left. And this is very much like that number that basically goes into the growth rate. It's the dynamo number minus a critical dynamo number is your growth rate. So what you're really seeing here is that there probably is, you'll notice there's no stars, there's no stars with Rossby numbers above 2 that are magnetically active, right? We don't see any X-rays from anything that's rotating that slowly. The sun is rotating about as slow as it can and still produce a magnetic field. So the hypothesis, and this is a very interesting idea put forth by Manfred Schissler and Robert Cameron, that the solar dynamo is really operating very close to its critical level. If it slows down a little bit more, it may just stop producing magnetic fields altogether. And the significance of that, if we go back to, and I apologize if this is sort of not something that people are familiar with, but there's this idea that if you're in a very complicated system, and remember we talked about things like even a string has many, many normal modes, many, many degrees of freedom, many, many ways it can change. And what's going to matter if those are unstable is how many of them are unstable. And if your growth rate, gamma, as a function of wave number, say, has a large region of positive places, then many, many modes are going to go unstable. And you'll have one of these problems where you have a superposition of many, many frequencies. When you get below the critical dynamo number, there's no modes that are unstable and the magnetic field just goes away. So if you're very close to critical, it is logical to assume that you might be in a state where only one normal mode is capable of undergoing an instability. So the dynamo is really only being driven by a single unstable mode. And one of the consequences of that is you're going to get oscillations at a single frequency, right? You have, if you didn't have any randomness to it, it would simply oscillate. And this is a picture, it's not a cartoon. This is a solution of a differential equation from Cameron and Schissler to a simple 1 degree of freedom problem. It's actually 2 degrees of freedom because it's a complex variable, which basically describes a linear instability, some nonlinear saturation term, and then they supplement this by saying, well, the ingredients in this dynamo come from turbulence, and so there's some amount of randomness that goes on. So if they put in some randomness, they get the kinds of long-term variations we see. So you could picture this as a sunspot cycle. This is not a real star. This is just a solution to this differential equation, but it's motivated by this observation that maybe there's only a single unstable mode in our sun that's at work. And that's why we have such a periodic system, okay? And that is also because the sun's Rossby number is rather high. In the other estimate, I had it at 10 to the minus 2, but at any rate, whatever it is, it makes a dynamo number that's very close to the critical level. So we have an oscillator, but it's basically barely able to sustain its oscillations. Let's now, in the little time that's remaining, talk about the Earth, the other dynamo that we tend to want to know about.
Hey, Dana.
Yeah.
Sorry, before you move on, so
Yeah.
Regu has I'm not sure which slide he's referring to because I kind of missed it.
Okay.
But so in a previous slide, a different trend below a certain Rossby number. Do we know what's causing that? So
Oh, I'm sorry. Yes, this is really interesting. Right. I think you're talking about this break. So
Yes, I am.
as the dynamo number goes up, the X-ray luminosity, the magnetic field in the stellar atmosphere is increasing, and then it just saturates. That's the correct word for it. Does anyone want to just shout out what the thinking is on what's really being saturated? This is still speculative because you can't really observe these stars, but the thinking is the sun has a couple of active regions on its surface at the peak, and as the solar cycle progresses, the number of active regions goes up. There are stars that are so active magnetically that their entire surface is covered with magnetic field, 100% covered with magnetic active regions. Once you've reached that, there's nowhere to go. Once you've filled your surface with magnetic field, you can't increase it beyond 100%, and that's why they call this saturated. This is thought to be stars that just have so much magnetic field that it's covered the entire surface. And even if you generate more magnetic field or more complicated magnetic field, it doesn't seem to increase the X-ray luminosity of the star. It's also that kind of saturation, I guess, is not as evident in this plot here, because this is a slightly different way of measuring the magnetic field, but it's really stands out in the X-ray luminosity plot. Is that what you're asking? Yeah, that's a very interesting bend in that curve.
Yeah, thank you.
Okay, so on to the Earth. We have our three ingredients. And actually, you can see from this cartoony cutaway a picture of the Earth, there's part of it that just isn't going to work for our dynamo. The part that we live on is not a conducting fluid, not a electrically conducting fluid, or at least not nearly well enough to do the job we need it to do, nor is the mantle below us that goes almost halfway into the Earth. That's all just not going to help us. In fact, it doesn't allow any currents to flow. So we can think that the current is zero, therefore the curl of B is zero. And we can write this as a gradient of a magnetic potential. Not a curl of a vector potential, but a gradient of a magnetic potential. This is just a consequence of having something whose curl is zero. And because div B is equal to zero, this magnetic potential solves Laplace's equation, right? And so a quick review, the way you solve Laplace's equation in spherical coordinates is with spherical harmonics. So this is the way, and actually I believe Carl Friedrich Gauss was the one who developed spherical harmonics, and it was for exactly this reason, to understand the complicated magnetic field of the Earth. It has to be expanded in spherical harmonics. The spherical harmonic L, if L is 1, you're talking about a dipole magnetic field. If L is 2, it's a quadrupole, etc. The radial dependence goes as, well, for the radial field goes as the radius to the L minus L plus 2. So the dipole field is going to fall off more slowly than all the other components, the quadrupole, the octupole, the hexadecipole. And that is, I think I'm getting ahead of myself because I drew this diagram from the outside in. The dynamo is working on the inside of the Earth. It's operating in this region that has molten iron, that is a electrical conductor, and it is turbulently convecting, partly because of heat, but also because some of the heavier elements are precipitating out into a solid, inner solid core. And that leaves behind material that is a little richer in silicon, I believe, the light elements. And that basically causes the light stuff has to rise up through the heavy stuff, and that drives the turbulence. So you have turbulence through the inner core here. That's our dynamo. That's where the magnetic field is being generated. And then the mantle and the surface, we see the multipole expansion of that. Okay, so we see a very simple magnetic field. In fact, if you look at the power in each of those L's, the dipole, the quadrupole, the hexadecipole, etc., if you look at the value, you see that on the surface that the dipole is a dominant component, and it may genuinely be dominant. I'm not going to get into too many details about this. I hope that Dr. Stanley will fill in what are very interesting but somewhat complicated details about why the dipole moment is slightly higher. But there certainly are quadrupole, octupole, hexadecipole, etc., moments present at the surface. And if you take into account the fact that they fall off with radius, and you correct what they should look like at the surface of the convecting core, is that really they should all have almost the same magnitude, maybe with the dipole being a factor of not quite 10 higher. But basically, what do you get when you add up a bunch of spherical harmonics over a bunch of different L values, all with the same amplitude? What kind of function are you going to see? Anyone? I would call that function a mess, right? It's the same as adding up Fourier components, which are all the same magnitude of all the different wave numbers. You just get white noise, right? You just get a very complicated tangled magnetic field. And that's really what you're going to see in the Earth's magnetic field, if you observe it where it's being generated at the core, not at the surface. At the surface, we tend to see a dipole magnetic field, and that's because mostly because the dipole magnetic field falls off more slowly with radius. So here is a picture of the radial magnetic field of the Earth. Okay, and so red are positive regions, places where the magnetic field of the Earth is coming out. You can see there's a bunch of those in the southern hemisphere, but there's also a lot of places where the magnetic field goes in. In the northern hemisphere, a lot of places where the magnetic field goes in, somewhere it goes out. Now, if anyone is puzzling over this, because this looks like a mess, you'll see in the upper right corner, I have graphed a little cartoon of the Earth, and the solid black line is the location of this image that I'm showing you. I'm plotting the magnetic field as it would be observed at the core mantle boundary, at the place just above the dynamo. And like I said, the dynamo on the Earth is really going to be kind of a mess. If I move that circle outward, here's a sweep, and we're going to start at 0.55 Earth radii, down at the bottom of the mantle where the magnetic field is being generated, and I sweep it outward, you'll see it becomes more like the magnetic field you're used to. You see only red in the southern hemisphere and only blue in the northern hemisphere. The magnetic field comes out of the south and goes up to the north. But that's only true if you're parochial enough to believe in the magnetic field only at the surface of the Earth. If you go higher up, if you go lower down, you see a much more complicated magnetic field. Okay, and that's really the same lesson we had from observing the sun, which is very complicated. All right, and let's see, what do I have to do here? This is how it has evolved for the last 100 years. You'll see there's some evolution, some places where the magnetic field is changing. But what's much more exciting is this is what it looks like if you plot the magnetic field at the core mantle boundary evolving for the last 100 years. And you can see there's all kinds of interesting stuff happening here. We have regions that are just moving one way or the other. And that's really the place where the magnetic field is being generated. And so the motion is really telling you about the dynamo. Okay.
Hey, Dana?
Yeah.
So Vicky asks, could different spots of the magnetic field direction within the mantle be analogous to how sunspots come in pairs? Or a loop coming back?
Yes, that's an excellent analogy. There are but for some reason, sunspots, the magnetic field of the sun, as far as we can see, not only is it being generated, but somehow it's being formed into these little strands. And the Earth's magnetic field, it's really because the Reynolds number, the magnetic Reynolds number of the Earth is significantly lower than it is on the sun, that kind of confined fibril nature people don't believe it's occurring in the Earth. So on a big picture, yes, you can have loops of magnetic field that are coming up and going back down again, but it's not, don't take the analogy too far. The loops are not confined the same way they are in the sun, if that makes any sense. One of the things I was going to point out here, because this I believe is done in the text, but certainly I think will be done by some of the lecturers, is from this original governing equation that I showed you, the induction equation. Well, now if we know B, and we sort of think we know eta, then it is possible to back out what the fluid velocity is in the core. And that is what people have done. They've made a few approximations to do this. They actually have ignored the diffusivity. And then they get values for, so those are the known things, and you can actually work out what the velocities are. And now you're seeing, you get basically motions that are 1,000 kilometers every century in some of these places. So that's not fast, right? 10 to the minus 4 meters per second. That's not the same kinds of speeds that even the sun is, meridional circulation is moving at. But it's enough. It's enough to do the generation of the magnetic field. And that's also the reason that the magnetic Reynolds number is lower in the Earth than the sun. But one of the things that we could say, oops, I thought I had back here. Let me do this. Did I not? Oh yeah, here we go. I just had them slightly out of order. So because of what we just said, the velocities there, 10 to the minus 4 meters per second compared to the sun. Here I've listed 1 rather than 10 meters per second. The length scales, the sun is bigger. And the diffusivities, the diffusivity is higher on the sun than the Earth. But what we get is a magnetic Reynolds number that is only 100 in the Earth. So that's not a really, that is a pretty diffusive medium. But what we're talking about is such slow turnover, right? If things are going at this 10 to the minus 4 meters per second, then, and the Earth is rotating once per day, then the Rossby number is 10 to the minus 6. The Rossby number is really, really low. And that means the dynamo number for the Earth is really, really high, even though the Reynolds number is also low. So one of the things, if we think back to why the sun has such a nice periodic variation, one of the hypotheses, and I like this hypothesis because it kind of helps us explain this too. Why isn't the Earth's magnetic field reversing regularly? Right, and here is the picture. This did come from the text. This is the orientation of the Earth's magnetic field. Just unfortunately, if they're going to measure it 20 million years ago, they don't have magnetic field measurements that go back 20 million years. So they measure the magnetization of iron in lava flows, and that gives them an up or down signal. Right? It basically tells you that the Earth's magnetic field is normal, course, we live in normal times. It goes from the south to the north, or it's reversed. It goes from the north to the south. And here is a classic plot of the orientation that this magnetic field has, normal, reversed, and it's just a mess, right? I mean, maybe this is a barcode, maybe you could scan it and you'll find out how much the Earth's magnetic field goes for on Amazon or something, but it's just a mess. And that is partly attributable to the fact that the Earth's dynamo is operating at such a high dynamo number that it's got a lot of normal modes that can be excited. And I'll just show you an image of the magnetic field in a simulation. And this is already a pretty old simulation by Gary Glatzmeyer and Paul Roberts, going back to 1995. This is just solving the MHD equations for the Earth's core. And you can see they've also included the region outside of the Earth's core, just to give you that north-south magnetic field we all know. But you can see it's a tangled mess in there. Also, you can see that the magnetic field of the Earth mostly goes from east to west, right? The toroidal magnetic field is very important in the Earth's dynamo the same way as it is in the sun's dynamo. It's just that, and so that this gets back, I guess, to, oh, I forgot who asked the question. These little loops you can see are jumping out and sort of connecting the same way sunspots would, but it's not fibril the way the sun's magnetic field is. Anyway, and of course, the magnetic field we see has to be the multipole components that exist with no currents, and that's just these kinds of north-south fields. Okay.
Hey, Dana?
Yeah.
Oh, sorry. So if you go back a couple of slides, somebody was asking, I believe they were asking about the South Atlantic anomaly, and that was what was posted in chat.
I'm not an expert at this, but the South Atlantic anomaly is just, the first thing to recognize is we have this expansion in spherical harmonics. And so the only, so the dipole of the Earth's magnetic field, the same way we derived it for the sun, is just picking out 3 of the spherical harmonics. But there's many, many others, and that's what gives us the mess here. The South Atlantic anomaly is just related to a low portion. Oops, let's go here. In the surface field, right? And so it's down here somewhere. Oops, I'll tell you one of the things I did. I actually go outside the Earth. So let's go down to the surface of the Earth. There we go. There we go. You see this big pink region in the South Atlantic. That's the South Atlantic anomaly. If we go deeper and deeper and deeper, you can see in the South Atlantic, there's a bunch of places where the magnetic field at the core is actually going the wrong way, right? By wrong, I mean in the south, the magnetic field is going into the Earth, into the core. By the time you get to the surface, it's not going in, but it's not coming out as fast. Does that? So this is just a natural consequence of the fact that the Earth's magnetic field is very complicated. Why it happened in the South Atlantic, I don't know. I think people have told me that if you look at this movie here, you can see from the core, this is 100 years ago, that the South Atlantic anomaly is evolving, right? I think, right, these regions of blue are kind of moving around relative to that. Does that?
I believe it's now, the South Atlantic anomaly is now in South America.
Oh, okay.
I believe that's the case, but yeah.
Okay, this is 2010, and yeah, it's quite possible. I know the Earth's magnetic field is evolving rather rapidly now, and I think this data I just took off a website. People here probably know a lot more about the data that's used in this. It is the magnetic reference field or whatever, and they had to update it. I think they update it every 5 years. They had to update it in off sequence because it was changing too rapidly, and they needed an updated field. But I'm sure people here know more about that than I do. So we have an activity that really asks for a general characterization of planetary versus stellar dynamos, flow speeds, rotation periods, stratification. I want to just open up the floor. If people did this, did you have any interesting observations about this comparison before you saw this lecture? Anyone? Okay, well, I think I outlined something that kind of combines flow speed, rotation period. I left out differential rotation and meridional advection. Those are more complicated in the Earth's field. We'll, I think, hear more about them from Professor Stanley. But the key point I was trying to drive home was the difference in Reynolds number and the difference in Rossby number. And actually, here is a synoptic plot of both the Earth's magnetic field, that's down here, and the sun's magnetic field, put on a similar size grid. So basically, the Earth's magnetic field is actually more difficult to measure. So we had to use spherical harmonics up to level 14, up to L equals 14. So in order to make a fair comparison, I took the sun's magnetic field at the surface and restricted it to L equals 14. You could see differences. The point I caught here, 2001, it doesn't have a large negative positive band along the poles. Anyone tell me why I'm not seeing a nice, I see a little bit of trace of negative, but it's not as strong as some other times. Why do I not see that sort of dipole structure in the sun's magnetic field here? Does the sun's magnetic field not have a poloidal magnetic field?
Not during the solar maximum.
Yeah, that's right. I caught it right as it's reversing. So this is the time when it's almost all toroidal. So that's not really a fair comparison. It would look a little bit more like the Earth's magnetic field if I caught it at solar minimum. Actually, it would look smoother than the Earth's magnetic field if I caught it at solar minimum. But otherwise, you can see kind of messy as well. The magnetic Reynolds number gives us some idea of the messiness. The Rossby number gives us more of an idea of how many different modes are being excited and therefore how complicated the frequency structure might be. So here's the Rossby number 10 to the minus 2, and it's an oscillator, and it's not a perfect oscillator, but it certainly gives you a feeling of oscillations. Here's the 10 to the minus 6, so a dynamo number, if I just square it, take the inverse of 10 to the 12 versus 10 to the 4, just very complicated. So this is maybe just being driven just above its critical threshold, and the Earth's magnetic field, the Earth's dynamo, way above its critical threshold. So that's why we're getting such complicated behavior. One explanation. I think I'm just going to leave us here. I do have some of the other planets. That was in the lectures. But since we're talking about long-term variation, unfortunately, while we have lots of cool planets with magnetic fields, you can see the Earth, even Mercury will have that. Venus and Mars really don't have that much magnetic field, some of these other things. But of course, we really don't know anything about the long-term variation of Jupiter, Saturn's magnetic field, Uranus, Neptune. So I won't keep going. It was in the lecture, but I'll stop it at sort of comparing the Earth and the suns. We have some understanding of long-term variability in both cases. One could argue the long-term in the Earth is not even really well defined because it's not a periodic system. But there's certainly a lot of complications. So I'll just leave it there and let anyone answer any questions, or we can go to office hours at some point and I can try to answer some more questions. Remember, this is not my day job. I don't study the dynamo. So here I am going to, oops, no, I don't want to leave the meeting. I want to stop sharing. Have I stopped sharing? Okay.
You have, yes.
I have. Okay, good. All right.
Why don't we take?
World magnetic model? Yeah, recent times due to more rapid shift. This is Regu has been updated before the 5 years. Not necessarily a new trend. Okay. Yeah, it might actually probably have something to do also with the need for particularly accurate data as that as things get more sophisticated. Anyway, the Earth's magnetic field is changing. What's a good way to explain to a non-physicist why the sun's field reverses regularly, why the Earth's doesn't? You know, I often use the analogy of an AC generator, right? The actual machinery they use to generate power is often called a dynamo. So the electric company has dynamos. Those dynamos are designed so really only one mode of oscillation is going to happen. The sun is not as well designed, but pretty much allows you to get an AC signal out of it. The Earth's magnetic field is just the dynamo is just operating in a way that's much more turbulent, I guess, for want of a better term, and it is not as regular. So I guess you just have to appeal to, hopefully they can understand that something that's really complex is going to produce a very complex signal, and the sun's magnetic field paradoxically is spatially more complex, but it really involves a sort of a simpler mode of oscillation. I guess that's the only way I can think to answer it.
I had a question, and this is something we were discussing in our Group 9's session yesterday, which you touched on, but I kind of want to talk a little bit more about it. I always kind of understood, it's pretty easy to understand conceptually, or at least put a picture in your head for why the magnetic field gets twisted up from a colloidal orientation to the other way around. But I have a hard time envisioning how it reverses direction. So how the polarity switches and we then return to solar minimum. And you said that it was because of the sunspot. Evidence for this, at least, is the sunspot's tilt angle reverses. But I have a hard time as easily comprehending the actual mechanism behind, because it's clearly not just advection.
It's not. There has to be something that subducts that magnetic field, the poloidal magnetic field, and essentially gives you a magnetic field that is in the poloidal direction, oriented oppositely, and therefore the toroidal amplification is going to be amplifying opposing fields. So what's going to reverse the toroidal magnetic field is that you've started to seed the differential rotation with the opposite sign of poloidal field. Sorry. And that is my understanding of how that works. Someone, does that make sense?
Is it really just like a cancellation type thing, like we saw with the Hale cycles?
It's a cancellation type thing. And the key ingredient here is getting that field back into the sun.
You're right. Yeah.
And that is done through the diffusion terms. To a certain extent, I think these models include downward advection, because this meridional circulation does close downward, although in a in a full 2D dynamo model, they would do that. they close downward. I'm not sure if that also is the dominant or if the diffusion is the dominant mechanism for getting the field inward.
Okay, great.
And someone is asking, Megan is asking about normal modes. And I hope some of our speakers, I'm thinking mostly of Nick Featherstone, will show us some of these dynamo models, especially the simpler models, the sort of mean field models. They do it and really do see normal modes show up, and they see cases where there are multiple modes and you get complicated field structures oscillating. I wish I'd included some of those, but it's a beautiful direction to go, but you can keep going that way for a long time. Oab stars, they don't have convective layers outside. The convection layer happens in the core. I honestly don't know anything about, there are apeculiar stars which do have magnetic fields. I don't know much about them, and I don't know what the story is for magnetic fields on O or B stars or A non-peculiar stars. So that's, if anyone there knows.
So,
Yeah.
no, I asked the question, but
Yeah.
what I was thinking was, so Earth's core is also producing a small kind of dynamo in comparison to the
Right.
stars like Sun.
Yep.
So do OAB type star have something similar to that? If anybody knows, because it's
don't
at the
know.
core. So that
Right.
was the only
So
thing.
they have
that
a
I thought.
convective core, so they could be
Yeah.
generating magnetic field in the convective core. The apeculiar, which have fields, I think are by and large dipole fields. So it does seem to make sense with what you say, but I can't say I know. Maybe someone out there knows about those aspects of magnetic fields. I actually know more about magnetic fields on neutron stars, but those are not generated by the dynamo. Those are relics of being in a star that had a magnetic field and then collapsed down to a neutron star. Oh yeah, so sorry, I can't say much more about that. Someone says there's one Rossby number defined for a star, and yes, that's true. It's different size scales, different convective scales, you get different Rossby numbers out of. And the ones the astronomers use are sort of a mean convective turnover time, tau sub c. I think I used a different one. Some of these numbers have, are not meant to be precisely defined. The same is true for Reynolds number, right? You have the viscosity is easy enough to know, but when you say length scale, if I look at my car, there's a lot of different length scales I could use to calculate the Reynolds number for my car. So it's not something you could define super precisely. Some simulations do, in the sense that they quote a single number that's based on the size of their simulation. But that's, again, just a choice.
So, Dana, should we go into like office hours and a break?
Sure.
Okay,
wanna-
so. Mhm.
Thank you all. In the morning, we began with the questions of magnetic fields on Earth and other planets. And Dana gave you a very nice introduction to some of the ideas that explain why magnetic fields in space and astrophysical objects are what they are. And the branch of physics that deals with questions like that is dynamo theory. And at its heart is a simple and a fundamental question. Why is the universe magnetized? I should tell you that when I first came into graduate school, and when I decided that plasma physics, as it was in the Department of Astrophysical Sciences at Princeton, where I was a student, was the area in which I wanted to work in. A question that had a lot of excitement going about it is why did the universe begin a finite time ago? And as many of you know, the answer to that question had to do with the Big Bang Theory, which was a break from the past. And I remember confronting that question or wanting to know what the answer is, realizing that the very tenet that the universe began a finite time ago was not consistent with a lot of important religious statements that were made to me on the basis of faith. And the very fact that scientists agreed that the universe began a finite time ago is enough to shake one to its foundations, to one's foundations. And that's what actually seeking precise answers to questions that are asked have great importance in our lives. And scientists don't know the answer to all questions, but sometimes they know some facts with a lot of certainty. And those facts can be transformational. In my mind, the question of why is the universe magnetized took a place as important as uh, did the universe begin a finite time ago? There was time associated with both. And in the question of magnetization, we are looking at long-term consequences in the life of the universe, which now we rate at something of the order of maybe 15 billion years ago. And even the time when I was a graduate student, the Hubble constant wasn't known to a great degree of accuracy. That became more and more refined as time went forward. So I remember the age of the universe moved from something of the order of 10 or 11 to 14 or 15 during my own lifetime. So we are looking at magnetic fields then on very, very long time scales, but not all astrophysical space or planetary objects have the same time scale. And it is important perhaps to recognize at the outset that it is just possible that we do not have one answer that fits all. So I'd like to begin by giving you a sense of the history of the subject and also the range of magnetic fields that we are dealing with here. For the Earth, as many of you know, that the magnetic field has been present for about 3.5 billion years. And now that Dana has very nicely introduced the very concept of ohmic decay, which she actually quantified, and I shall return to that somewhere in my lecture, that's about 10,000 years. So the fact that the magnetic field of the Earth has endured for 3.5 billion years when the ohmic decay time is just 10,000 years does raise the question of why is this magnetic field present? Because at all, because if it were just subject to the wear and tear of diffusion, then it would have been gone a long time ago. There's also strong variability of 1,000 years in the Earth's magnetic field of changing polarity and so on and so forth. So we are really talking about two different timescales here. One, of the presence of the magnetic field for as long as it has been around, and then of course, over a shorter time period, changes in it. And this overall feature is actually duplicated in Mercury, Jupiter, Saturn, Uranus, Neptune, and Venus at one particular point did have magnetic fields that went away. And that makes Venus a fairly vulnerable planet in terms of how it would respond to space storms, or how life on it would have responded to it if it was ever present. If you move on to the sun, from the Earth and the planets, you have magnetic fields from smallest observable scales to the size of the sun. And this beautiful 11-year cycle of the large scales magnetic field, the 11-year cycle that continues in many minds to be a mystery. And what I am talking about here are two levels of problems. And the field is still quite open for many of you who would venture to get into it, are in it already. That you have these long-lived magnetic fields, some spanning billions of years, and superimposed on it, on this existing magnetic field, an 11-year cycle of the large-scale field for the sun. Beautiful in its regularity, and as yet not completely understood. The ohmic decay time, if you should neglect the effect of turbulence, is 10 to the power 9 years. So that's significant, but the magnetic fields are actually present for much longer. Once again, you need a mechanism. Other stars, if you move away from the sun, and in many ways, the sun is a typical star. Some have outer convection zones similar to sun, and Dana referred to this in his talk. I was not there for both parts of it, but I certainly know that he had a slide where he addressed this issue. And then there are stars with primarily radiation zones and no convection zones at all. And without a convection zone, it's really hard to make the case for a dynamo. And many of these stars, if they have magnetic fields, were most likely primordial. And this goes back to a question that was just asked during the break about the mechanisms that enable the amplification of the magnetic field. But it must have started from a seed. And it is just possible in some cases in space and astrophysics that what you have is no dynamo at all, but merely the persistence of a primordial magnetic field, which might have been generated by some seed mechanism, such as the Biermann battery. I won't have the time to dwell on this, the so-called Biermann battery, but when the appropriate time comes, I'll point to where it comes from. And I can take questions on it later on. Galaxies, there are two schools of thought on this, and that's primarily got to do with numbers. I mean, galaxies do have micro-Gauss magnetic fields. And there are some who feel that the dynamo mechanism is not as strongly operative in the galaxy as it is for some of the planetary bodies that we are referring to. And that is just possible that the dynamo in a galaxy is just not as strong. And probably what we have is the remnant of a primordial magnetic field, but that is a subject of some debate. So I hope what I've conveyed to you is that there is a large number of astrophysical objects in which it is important to invoke some kind of a mechanism, which we call the dynamo mechanism, that will account for the fact that you start with small scale magnetic fields, and in many cases, weak fields that are amplified to what they are today. Since Dana gave you such a nice introduction to the subject, I'm just going to plunge right in. And I'll say that the common point of departure in understanding the dynamo, and without any apologies, I'm going to show you some equations, because a lot of the work in dynamo, that there is some that is analytical. Early years, there was a lot of analytical work, and there still is. But sophisticated computer simulations have now become a primary weapon of use in understanding dynamos. And that is because the governing equations for magnetic fields, at least at a first approximation, are the equations of magnetohydrodynamics, which are like the Navier-Stokes equations are in fluid dynamics, except that they're modified by the presence of magnetic fields. So the first equation, del rho del T equals minus del dot rho V, is the equation for mass continuity. The second one, just below it, is the momentum equation, which has scalar pressure. That's an assumption. Gravity, the Lorentz force J cross B, and a viscous tensor that I will explain to you later on. Then there is an equation for the internal energy or the pressure. And on the right-hand side, you have transport terms like the thermal conduction, viscous dissipation, ohmic dissipation. And last but not least is the Ohm's law, which you've already seen Dana talk about, which has a resistivity term. Now, if you look at a text in plasma physics, you will find that there are, in fact, additional terms in this Ohm's law. And one of those terms is called the Biermann term, which is the gradient, which is the curl of the term gradient pressure over n, roughly speaking. So if you finish taking the curl, that'll end up being curl P cross curl n. So if gradient pressure and gradient density aren't perfectly aligned, you have actually a finite contribution from that term. We are neglecting that term here. It can play a role in the early life of the dynamo, and that is the term that is referred to as Biermann battery. So the implicit assumption here is that the Biermann battery term was there somewhere in the early stages of life of these astrophysical objects. It produced a seed magnetic field due to misalignment between gradient pressure and gradient density. Then that then got amplified through the dynamo mechanism, which we will make precise in the rest of this talk, and came to where it is. So once that has played its role, you don't need to worry about it. I should add right away that that's an oversimplification. One of my own graduate students who graduated a couple of years ago pointed out by doing careful work that the Biermann term by itself not only plays a role in creating the seed, but under certain conditions can also mediate dynamics that comes thereafter. But in order for that dynamics to be observable, you must have this misalignment between gradient pressure and gradient density, which doesn't happen in many cases, but it does happen, for example, in high energy density matter, laser-induced plasma experiments that go on in national laboratories like Lawrence Livermore or the University of Rochester, where people have studied the Biermann effect in depth to understand how magnetic fields can be spontaneously generated and can play a role during the entire dynamics. But for most practical space and astrophysical applications, these effects are not deemed to be very strong. So people just drop the Biermann battery term and just deal with the MHD equations. And this is of course assuming that fluid equations work. And it's important to know that this is an assumption, because when you get out to systems in the universe, a lot of them are so tenuous that they're virtually collisionless. And there, the question of validity of MHD equations is open to doubt. So how do you understand magnetic field generation in such systems? There is a lot of new work now trying to address these problems from kinetic theory or using particle and cell simulation codes, which are not yet powerful enough to deal with large systems, but produce very valuable insight. I'll have nothing to say about that, those efforts, which are still fairly in their infancy, and a very nice review paper, which actually is a modern review paper by Francois Rincon, who is at CNRS in France. You can look it up, Rincon, Francois is the first name, has a significant section on what are called collisionless dynamos that I'll have nothing to say about. Furthermore, the dynamo problem is not just a problem that is describable by non-relativistic equations. You should, when you go to compact objects like neutron stars or black holes, which show extremely strong magnetic fields, the dynamo problem there is in a very different regime than they are for many of the objects that we'll be talking about in this lecture. And there you have to use relativistic versions of these equations, otherwise known as general relativistic MHD. Such codes exist in the astrophysics domain and is what is used to study magnetic fields in compact objects. We are not going to go into that. We're going to deal with non-relativistic motions at low frequencies where typical velocities are much smaller than the speed of light. Okay? And now for all these tensors and stuff like that that were sitting there, I just want you to see this. And by the way, this slide is taken directly from Matthias Rempel slides, who is one of the best simulationists we have in the solar community, who's actually coded up these equations. So you should know what he coded up. So this is his viscous tensor, his other tau ik as well. This is the rate of strain tensor. This is the viscous tensor. The ohmic dissipation term is written here. The equation of state is written here, where nu, eta, and kappa are viscosity, magnetic diffusivity, and thermal conductivity. And the mu0 stands for the permeability of vacuum. Everything is written here in NKS units. Okay, this is just for complete, just so that you have complete knowledge. The codes have these terms in them, and they attempt to capture realism as much as they can. I want to get back to the induction equation, because the induction equation is what Dana also told you a fair amount. And where did that come from? It came from Ohm's law, the ideal MHD Ohm's law that Hannes Alfvén wrote down, E plus V cross B equals 0. But now on the right-hand side, you actually have a contribution from the ohmic conductivity. 1 over sigma is nothing but eta. We use either symbol depending on what you want to do. I oversimplified a little. Eta is proportional to 1 over sigma. There's a permittivity constant. So you can use any one of these. It's typical to use eta. And if you take the curl of E, okay, so this is really E plus V cross B equals eta J, but J is written according to curl B equals mu0 J. You have this. Now you take the curl of this and you use Maxwell, which gives you curl of E equals minus del B del T. You can eliminate E out of the problem completely, and you're left with the induction equation. Del B del T equals curl cross V cross B minus eta curl cross B. And if you take the curl cross B, since divergence of B is 0, you can write it as a diffusion term for the magnetic field. And you know all of this. And you can actually write everything in terms of dimensionless coordinates. That is, take all your length scales in this problem and divide it by a typical length scale L, which could be the system size. And the velocity you non-dimensionalize by dividing by a typical velocity scale. And the typical time unit you can divide by L over U. And if you do that, as you saw in Dana's lecture, you can write the induction equation in dimensionless form. Will you make sure that you ask me questions if there is anything that I'm being obscure about? Any questions yet? I can't see you because all that I see is slides.
And there's nothing in chat, so please,
Okay.
you could either interrupt the lecture or just type in chat. I'm monitoring chat.
Thank you, Dana. And please feel free to interrupt me. I like questions. Okay, so if you write this in dimensionless form, you get this. And a pivotal role in this equation is played by this quantity, the magnetic Reynolds number, UL by eta. Eta is typically a very small number. If you use the classical resistivity estimates, say given by Lyman Spitzer in his book, He wrote one of the first books in plasma physics. He was the founder, as many of you know, of the Princeton Plasma Physics Laboratory because he was deeply interested in the problem of creating thermonuclear fusion, the energy source that powers the stars. And that's a separate subject in itself. But he also created the Department of Astrophysical Sciences at Princeton. So he had enormous range of scholarship. Anyway, he wrote one of the best plasma physics books of all time, his initial monograph on it, full of intuitive, good arguments. So if any of you would like to pick up the rudiments of plasma physics, pick it up from Spitzer's book, and you will see that he did define a dimensionless number like what you have. Now, if typically this eta is very, very small using Spitzer's value, and Rm tends to be a very large number. And you notice something very curious about this equation. It is curl cross B. So if you write out curl cross B using vector identity of gradient of divergence of B minus del square vector B, you end up getting 1 over Rm del square of B. And if you look at del square of B, that's got the highest spatial derivative in the problem. And it is multiplied by an extremely small term, 1 over Rm. So your first inclination, if I am naive, I would say, who cares about this small term? But you immediately recognize that you have to be careful about that because even though 1 over Rm is very small, what you have here is the second derivative of the magnetic field. So if the magnetic field gets very wound up, where you get a lot of high current densities, but the second derivative of B is larger than the first derivative, even though it's multiplied by a small number, you have to be very careful. That's what is called in mathematics a singular perturbation problem. And singular perturbation theory, you have to be very careful about because you can't just use normal power series expansions and say, I'm just going to throw out that term because the term that is multiplying it is very small. And that's why dynamo theory is a very interesting mathematical problem too, is that you really have to keep this all in because the smallest term is multiplying the highest spatial derivative in the problem. And that's usually a sign of trouble. So be very careful. So it's linear in B, that's very nice, but it's called this singular feature. Now, if Rm is much smaller than 1, what I just said does not apply, then this term is really large. 1 over Rm itself is a large number. And suppose you are in the realm where then this term is large and this is much greater than curl cross V cross B. Then you are in what is called the diffusion dominated regime where convection isn't playing a role. So this almost looks like a metallic conductor, right? If you have a metallic conductor and you have a magnetic field in it, and that metallic conductor has some finite resistivity, no matter what magnetic field you give it, that's just going to decay in time on a typical diffusion time scale, which you can estimate by simply replacing the nabla operator, which is a Laplacian, by 1 over L squared. So the time scale is L squared by eta. And this was in Dana's lecture. And this is what we mean by the diffusion time. If anybody is telling you about estimating the diffusion time in the Ohm's law, that's what they mean. What is interesting about plasmas is that they can have strong convection. And this is why the plasma problem is different than the problem of a static conductor in which the magnetic field just decays. If Rm is much greater than 1, and you can throw out the dissipation term, then you're back to the ideal MHT limit, in which case you can expand out curl cross V cross B using the vector identity into 3 terms. And there would be a 4th term, which will be velocity multiplied by the divergence of B. But since B is divergence less, you have 3 terms here. And each of these terms have a physical meaning. The V dot grad B term is essentially the term which you could move to the left-hand side, and it will be del del T plus V dot grad on B. It's all it's a total derivative working on B. So if you're following a fluid element, the history of the fluid element along a magnetic field, these two terms will describe that. The second term is amplification by shear, and this is stretching of field lines. So very much the rubber band analogy works here. If you think of the magnetic field as a rubber band, and if you really stretch it, you can strengthen the magnetic field, and that's what is amplification by shear. And this term is amplification by compression, because if del dot V is 0 for an incompressible plasma, that term will drop out. In the absence of it, if the term has finite compression, it has the potential to amplify the magnetic field. So this is just the physical significance for the various terms in the ideal MHD Ohm's law. So we now have a clear-cut motivation for dynamos then. For V equals 0, you have nothing but diffusion. And by the way, as Dana pointed out, that resistivity that is sitting here, I talked about the Spitzer formula giving you a value much smaller, and whether the Spitzer resistivity really holds or not is not at all clear, because if a system is very turbulent, then it's very likely that turbulent will do something to dissipation in the system. But this problem has a lot of subtlety in it. A point of view that many people who believe in codes more than I do would simply say, why are you worried about the small eta? It's never really the Spitzer resistivity anyway, because you've got turbulence, and all that turbulence will do is to give you the enhanced eta you want. Well, that's an assumption, in my opinion. It's plausible, but needs to be proven. And there are many cases in plasma physics where this naive assumption has proved to be wrong. That is not to deny the existence of turbulence, but actually ask yourself the question whether turbulence always produces an anomalous dissipation exactly where you need it. That's the job of theory, to prove. And in many cases, what happens is that the kind of turbulence we're dealing with is actually not in the MHD variety, but at a much more smaller scale in the kinetic variety, especially in collisionless systems. And then the question is, does that collisionless turbulence conspire to give you an eta that you can put in an MHD code? Sometimes the answer is yes, and sometimes the answer is no. Beware. Therefore, don't just buy into anybody's telling you that somehow nature will manufacture the eta you need by creating a turbulence. That's good for hand waving, but it's not always good guide for physics. So we'll be careful about that. Right now, unless I state otherwise, I'm really referring to eta in a sense where we can quantify it by the Spitzer formula. So think of that as an irreducible resistivity in the system. And it might be greater, it might be that, with or without turbulence. And we already have talked about this. In Earth and other planets, you know that you need a dynamo. And permanent rock magnetism is not possible because the temperature in the Earth's core exceeds the Curie temperature, and the field is highly variable. So if you put this all together, you must come to the conclusion that there must be a dynamo that shows how to generate large-scale magnetic fields. We don't understand it yet. The evidence is overwhelming for Earth and other planets that that must be so. Sun and other stars, the evidence for solar magnetic field is for 300,000 years based on beryllium measurements. And the sun is a typical star, but not the only star in the universe, as you well know. Most solar-like stars show magnetic activity independent of age, even though our knowledge of these stars' magnetic field is not as detailed as it is in the sun. You can give pretty good and reliable estimates of what the magnetic fields of stars are and their correlation with age and rotation. And there is, one can say, indirect evidence. In the sun's case too, if you go very, very close to the corona, solar probe will get the closest that we can to the sun and will tell us about magnetic fields, but nothing in the sun's magnetic field is as well measured as they are in the Earth's magnetosphere, where you have magnetometers doing in situ measurements. So there is an element of inference regarding magnetic fields for the sun and other stars. So that's why I use the word indirect evidence for stellar magnetic fields over lifetime of stars. But the dissipation is about 1 billion years. Now, primordial fields there at the moment of their birth could have survived in the radiative interior, but the convection zone is really churning with turbulence all the time. And this is where, if you invoke the concept of turbulent diffusivity, that's about 10 years. So you look at all this and you say, yeah, in some cases, primordiality might be a good explanation, but in most cases, this is not the case. And I think I can make that point with some amount of clarity and still leave room for some special astrophysical objects where the field might well be primordial. Some numbers. If you look at the Earth, the sun, and now we show two scenarios of where you have the plasma conductivity, the turbulent conductivity, and what does it take to get dynamo experiments going in the lab. And I won't dwell on it. These are the values of eta, L, and U, but I will bring your attention to the magnetic Reynolds number. I like dimensionless numbers, like all physicists do, because that's independent of scale. The Earth, the RM is about 300, and diffusion time is about 10,000 years. So you need a dynamo. In the sun, the magnetic Reynolds number is about 10 to the power 9 years. Yes, if you believe in Spitzer resistivity, it's a bit of a judgment call, but not really. Even then, the sun's magnetic field is longer lived. If you have turbulence, as I just pointed out, you have no prayer but to rely on a dynamo. And liquid lab experiments have this sort of a diffusion scale. And these experiments have had some level of success in investigating mechanisms of what produces large-scale magnetic fields, but no definitive ones yet. It's very, very hard to do good dynamo experiments in the laboratory that are applicable to planetary systems. And the largest experiments right now is in Germany. It looks very promising. And there is another very nice set of experiments in the University of Wisconsin-Madison by Kerry Forrest, which is also trying to break new ground. Now, Jenna, how am I doing with time?
It's 5 minutes of noon here.
So how far am I from break?
Oh, good question.
About 20 minutes?
Nick can.
About 15 minutes.
15
Okay,
minutes,
thank you.
okay. So I want to make precise. Any questions at this point so far? I've either lulled you to sleep or I'm totally clear. Which one should I believe? I want to hear from a student.
It's clear.
Clear so far?
Yeah.
Good. Not too elementary, I hope. Should I go
No.
faster?
Actually, I have one question.
Please.
So going back, you showed us that the diffusion time for Earth is around 10 to the 4 years, and
Yeah.
yet we have measurements of a magnetic field that exceed that time. So
Right.
there has to be a dynamo.
Right.
But then could you just go over one more time why we know there has to be dynamos for stars when those diffusion times are so large?
So as I said, there are some cases where you can in fact argue that what you are seeing could actually be primordial. I mean, if you look at the plasma resistivity question, even for the sun, the RM is 10 to the power 10 and diffusion time is 10 to the power 9. We're still talking about, 10 to the power 9. So the sun's age is several billions of years, right? For 3.7 or longer. Dana, am I having that right? How many billions of years is the sun?
5 billion,
4 more.
4.5, 4 and change.
Right. So you could say then, if you believe in the plasma conductivity, a factor of 4 or 5, is that enough? I would say it is, that you have to think about a dynamo. But then the more ominous possibility is, ominous or happy possibility, depending on whether you're a theorist who likes dynamo theory or not. I like to worry about the problem because it's a great physics problem. But if you think of turbulence, it should have decayed a lot earlier, right? So this gets back a little bit to the question of how well do we know this dissipation coefficients? And the real fact of the matter is not too well. And so that's where the uncertainty lies. You see what I mean? And the similar thing would be true for stars as well. Is it a factor of 5 or 10 or several orders of magnitude? Have I answered your question?
Yes, thank you so much.
You're welcome. So I want to make a clear distinction between two types of dynamos. In one type of dynamo, I think we more or less know most of the answers. And there are big questions about the other kind of dynamo, the really important kind of dynamo, which I'll call the large-scale dynamo. But let's make this precise. So what do we mean by the dynamo problem? In the original mathematical definition of the dynamo problem that got all the mathematicians truly excited about working on dynamo theory is that they loved the fact that they didn't have to deal with the complexity of MHD theory, that the entire problem was a linear problem in magnetic field. You look at the induction equation, everything is linear in B. Everybody loves linear differential equations because they think they know how to solve it, right? So imagine a planet S, bounded volume with a surface delta S, and B is maintained by current contained within, where in the long distance, B is decaying like a dipole field typically does. So within the object, you have Ohm's law. Outside, you have a vacuum field. The magnetic field jumps across the boundary, Maxwell's equation, del dot B equals 0. This actually comes by just integrating this over a box. V is 0 outside of S. Assume that n dot V0 on the boundary. Then you can define the kinetic energy. The kinetic energy is half rho V square, and imagine that it's a finite energy system. You don't want to deal with infinite energy systems. It's a separate mathematical issue, but imagine that the kinetic energy of the system is finite and bounded from above by E max. So a mathematician's definition of a dynamo would be V is a dynamo, V causes a dynamo if an initial condition B equals B0 exists so that E magnetic that eventually occurs in the system when integrated over a certain volume would produce energy that is larger than energy than you started out with. Okay? So basically the focus was, if you have an initial magnetic field, initial energy that you start out with, eventually the magnetic energy, and energy again, not flux, that exceeds by far the energy that you started out with. Now, in a typical problem like this, the magnetic field is quite turbulent. So imagine that you decompose the magnetic field into a large scale part and a small scale part. The small scale part actually represents the energy of the turbulence. So if you simply write your E magnetic, which is total B squared, then you have B bar square plus B prime squared. These are positive definite terms. But then there's a cross term, B bar, B prime, and that does not have a definite sign. So B prime there is fluctuating, and if you're taking the average over a volume, you could define the average to be such that when you define it over a scale intermediate between the large scale and the small scale, the cross term will drop out, simply because square terms persist because they're positive definite and the cross terms drop out. Now, this is an important distinction. What is a small scale dynamo and what is a large scale dynamo? A small scale dynamo is where the energy in the mean field squared is much less than the fluctuation energy. So when a small scale dynamo is active, then you start out for a seed magnetic field and the system goes turbulent. There's a hell of a lot more energy in the turbulent fluctuations than there is in the energy of the mean field. What does that physically mean? It physically means if you associate a mean large scale flux, right? And if you take an area, then typically that magnetic field will generate a lot of flux. But if your energy in the mean field, B bar square, is so much smaller, that field is not going to have a lot of flux. Not in the mean field. So that's why it's called a small scale dynamo. In short, in the small scale dynamo, the fluctuation completely overwhelms any possible mean field. The large scale dynamo is different. It's the opposite of the inequality, whereby the mean field energy is comparable to the fluctuation energy or much larger. So almost all turbulent or chaotic velocity fields are small scale dynamos for sufficiently large Rm. This is the characteristic of MHD turbulence. You're not generating a lot of mean flux because you're not getting a lot of mean field. What you're getting is a lot of fluctuations varying in space and time with a lot of energy, but not that much mean flux. Large-scale dynamos require additional large-scale symmetries, and I'll get into in the second half of this lecture and what we know. Large-scale dynamo problem to this day is largely unsolved problem. In the very nice examples that Dana gave you, you were seeing large-scale dynamos, say in the homopolar or Babcock-Leighton, but you have to, not the homopolar. The homopolar was electrical engineering. That's a homopolar generator. It's got nothing to do with plasma physics, but it's got very great intuitive appeal because it embodies in itself some of the principles that are responsible for the dynamo effect, but no more than that. And the Babcock-Leighton, it would be great if Babcock-Leighton actually works, and that remains to be proven. And one has to prove that out of an MHD turbulence situation, you will have the Babcock-Leighton mechanism emerge as a solution. And that still remains to be done. It's interesting that such a model even exists for us to aspire to get to it, but I should let you know that the task of getting to it is still an unsolved problem. So what does it mean to have large and small in practice? So this is a full disk magnetogram, Solar Dynamics Observatory, the HMI instrument on board. And you see this, okay? If you go to greater and greater granularity, you will see a lot of structure. And then you will see large scale structure like this sun's overall dynamo field or the sunspots, which are evidence of large scale magnetic field growth. In the sun then, both of these coexist. And the dynamo problem is a living problem to be solved. Furthermore, as shown in this beautiful movie, if you look at the sun's rotation and the way the sunspot is, and this has been done by David Hathaway, who put together this wonderful movie. And what you're really seeing in yellow and blue is the magnificent 11-year cycle where the sun starts out with magnetic fields, it goes to zero, it reverses sign, and goes the other way. And you can keep staring at this movie, and you've got two things to account for. You have to account for the large-scale structures you see, as well as for this beautiful 11-year cycle for which definitive explanations do not exist. Though yesterday in a conversation, Dana was telling me some very interesting results that have come out of our most recent winner of the Hale Prize, and so on and so forth. So don't let me paint this landscape as a bleak one. There are some who believe that they have found some partial answers to this puzzle. But on the whole, I think it would be a fair statement that a truly believable picture, even though right now it seems not quite in our grasp, would be to show how we start from the equations of MHD, come to large scale structure, and have the large scale structure show that cyclic behavior. I don't know whether any simulation would ever be powerful enough to do that, but it'll be really nice to make theoretical models in which analysis and simulations go hand in hand to at least where we can understand the principal features. This I will not dwell on that much because you already know this mechanism. And in fact, it was very nice that you did the exercise you did where you actually estimated. So this is the classic stretch, twist, fold dynamo. And I should let the comment that I would like to simply make though, that all these things were based on pure exercises, not of the MHD equations, but of the induction equation only. And mathematicians were very involved in this exercise because the B equation being linear, the problem that they chose upon themselves to solve, if I may just remind you, and for a long time, this is what the game was. Let me specify a velocity field, and I'll just specify it. And let's hope that nature will be creative enough to manufacture it. If I give a velocity field, how does my magnetic field behave? I call that problem the kinematic problem. It's not the fully self-consistent or dynamic problem, because there what you're assuming is that your velocity is prescribed and the B that you are generating is not strong enough to change it. MHD equations tell you that this is a two-way traffic. If B changes, it changes V, and changes in V induce changes in B. But that back reaction of the momentum equation and the induction equation is not included in the kinematic problem, nor in this simple picture. The simple picture has it right in the following sense, that these are the kind of things we must go to morphologically in order to get dynamics. But to say that the induction equation controls all of it would be an oversimplification. But it has some of the basic instruments, namely basic ingredients. You have amplification through field line stretching. You have twist fold required to repack field into original volume, as you did. And then you have reconnection. And actually reconnection means these two pieces bit off and they form this sort of a thing. Now reconnection is, if you didn't have reconnection in a problem and that eta term was not there, what's going to happen is, if you just kept twisting, but without reconnection or breaking, what will happen is that you'll get the magnetic field into a horrible tangle without respite. Try this out. Take a newspaper, a morning newspaper, and fold it, okay? Then fold it back on itself here and try to do it again. You will find that if you get through 2 folds, you're lucky. What really happens is, unless the newspaper has a way to break, the tension builds up so much that you will never get into this indefinite exercise of twisting. So reconnection has to be there to avoid a horrible tangle. And so I have to just say a few words about magnetic reconnection, but I won't dwell on it. This is a subject that very near and dear to my heart.
Amitava, I think we're due for a break. Do you want to take a break before we try to tackle magnetic reconnection?
I'll tell you what, let me just introduce magnetic reconnection and I will do so very quickly.
Very good, okay.
So thank you, Dana. What is magnetic reconnection? Remember I said nothing on the right-hand side of the Ohm's law. So eta j has been dropped. So if you took its curl, you would get del B del T minus curl cross V equals 0. And reconnection has, or the absence of reconnection, first talked about by Hannes Alfvén, is this Alfvén's theorem. It has two forms. One is that suppose you look at a plasma fluid and you paint a circuit in it, okay, and magnetic fields are threading it. One of Alfvén's theorems says, of course, that this element that you took initially will of course deform, and will deform much more horribly than what I have shown here, which is drawn after a very short period of time, like putting milk on coffee. You know, it forms all kinds of vicious twists and whorls and tendrils. So is this going to be in the hands of a plasma. But there's an invariant in the problem, which is, as Alfvén said, the flux threading through this ribbon, no matter how deformed it gets, will remain constant for all times. That's one variant. The other is, imagine you have a field line. It's a fictitious line that you draw, but you know how to do this. You draw a field line. Michael Faraday told us how to get field lines by using iron filings around magnets, and they line themselves up nicely. So imagine you have such a field line on which there are plasma elements. Alfvén's theorem says that if the field line is moving with the fluid, and every element does, following the induction equation or the MHD prescription, then the field line can change, but if you have initially fluid elements on it, every fluid element will remain tied to the field line like beads on a wire. And that is what is called the frozen flux behavior, flux line behavior in plasmas. In the presence of resistivity, this behavior is completely destroyed. Field lines can reconnect. Flux is no longer through a particular circuit invariant because the circuit itself deforms. And certainly field lines with plasma elements which are tied to a field line are no longer obliged to stay on it. And I'm going to end this session by just telling you that, take my word for it, how rapidly this can actually happen is now a reasonably well-solved problem. It is possible to get fast reconnection through a number of mechanisms where I put on the right-hand side R, which can stand for resistivity or other collisionless mechanisms, which can give you reconnection rates of the order of 1/10 of the Alfvén speed due to a number of ways that you can get there. And so at least people know how to get fast reconnection. So one of the ingredients of dynamo theory that you must have reconnection occurring, of course, has to be tested case by case. But just for the purpose of this talk, we will assume that reconnection is there, that fast reconnection that is not too sensitive on resistivity is possible, no matter what the picture, be it resistive MHD or other collisionless mechanisms. And with that, I'm going to take a break and we'll get back into slow, fast dynamos. How long should the break be, Dana?
10 minutes. So we'll get back at 25 past the hour.
Thank you.
I think that just gets us almost at the same time as we're supposed to be.
I'm running about 5 minutes late.
Yeah, that's okay.
All right.
I think we all started about 5 minutes late, so.
All right. Thank you,
Yeah,
Dana.
thank you. Very nice. Okay, I think we have, it's 25 past on my clock. So Amitava, why don't you start up again?
Oh, I had to unmute. Thank you all again. I'm just going to start with a slide that you've already seen more than once in the summer school, but I'm doing that for reference. So the dynamo mechanism at a pictorial level, we had two sets of arrows here. One had to do with first twisting it, then folding over it. By doing that, you have a little kink where you fold over. And when I was giving you the newspaper analogy, I wanted to convey to you how hard it is to get past that kink, because once you fold and get a kink, to refold it is not easy. But anyway, the kink is not something you can live with, because that's what leads to tanglement. And what you want is some reconnection here to pinch this off so that you get two loops of double the strength. Or you could have gone through the path where the reconnection occurred first, and then the repacking occurred, and you came to this. It turns out that this cartoon illustrates the distinction between fast and slow dynamo. And that's what I am going to do at the very beginning of the lecture today, that the magnetic diffusivity can have a strong effect on the growth of magnetic field. So you're looking at this induction equation, okay? So it's a linear equation in B, and you say, all right, I will posit a solution where B goes like some quantity B0, which could be dependent on space, but weakly dependent, say, multiplied by exponential gamma t, where gamma is the growth rate of the dynamo. The fast dynamo would be the one in which the growth rate would be independent of Rm, in which Rm is there, because as you saw in both scenarios, there must be some form of reconnection. Main question is, what is the dependence on Rm in that process? And the stretch, twist, fold mechanisms, the attempt was to put all the action on the stretching, twisting, and folding based on chaotic flows that could do that very efficiently, so the dependency on Rm became very weak. This was what was called fast dynamo. The slow dynamo was where the growth rate was much more controlled by resistivity, some fractional power of Rm. And a lot of dynamo theory at its very inception was essentially reduced to a search of fast dynamos, because people did want to get to regimes where the effect of eta would be as small as possible. So since that's where most astrophysical objects were, where Rm was much greater than 1, fast dynamo searches became very important, and the entire problem boiled down to who can come up with the best kinematic model given a certain V, so that we can say we have a fast dynamo. And a lot of progress was made on that problem. And they all relied on some form or the other for reconnection to become weakly dependent on eta. And one can go over a whole lecture by itself, and I usually do that in other summer schools, but not this one, on how reconnection is very controlling in terms of what it does for huge events like flares or CMEs or others, or for Earth substorms and so on and so forth, but also more subtly in the dynamo problem. But here we, as I said before, we are assuming that, and I think it's a good assumption, that we can get reconnection rates that are reasonably fast based on our current understanding, which is weakly dependent on Rm. All right, now let's go and look at in some depth at the dynamo of the sun. And I will return to kinematic dynamo theory and its limitations a little later in the talk, because it turned out that the kinematic dynamo theory gave us, I think, an overly optimistic view of the efficiency of the dynamo mechanism. And when we started talking about the full complexity of MHD, as it now in many of the codes, it turned out that the picture was a lot more complicated. But before we get into that complicated picture, I want to talk to you about solar structure And just amplifying on some of the things that you have already seen, this is the core reaction in the sun is proton-proton reaction. That's where you have the hottest temperatures that radiate out. And you have a big radiative zone around the core. And then there is a convective zone. And what is one of the remarkable discoveries of helioseismology is that there is a very thin layer that separates the radiative zone from the convective zone. And it's called the tachocline, using a term that Edward Spiegel of Columbia University first concocted. And he did so without even knowing, he was a visionary, without even knowing how thin that tachocline was. And it turns out that helioseismology has now shown us that's less than 5% of the solar radius. And why the tachocline is there is still a mystery of solar physics. But the region that is really vital is what goes on at the tachocline and the convective zone in order to understand. And there is where you have a lot of velocity. As you know, the plasma is moving around. And we'll be dealing, without even understanding the tachocline, we'll be dealing with the problem of the dynamo going from the edge of the radiative zone to the upper reaches of the solar corona. So now we get into a little bit of math. I'm going to be quoting results, and I don't have the time to go into it, but you're entitled to the facts. So take it from me that if you assume that the sun is axisymmetric or toroidally symmetric, Dana already introduced to you the notion of the toroidal field, which is in the phi direction. And then there is a poloidal field, which, because of the existence of the symmetry along phi, can be written in terms of a flux function A. So the nice thing is then you have built into the magnetic field two nice stream functions, which make the problem a little bit easier. The velocity has a radial component, a poloidal component, and this dominant toroidal rotation, the solar rotation. The differential rotation represented by this term is in fact the most dominant shear flow in stellar convection rods. The meridional flow is a byproduct of the differential rotation observed as poleward surface flows. And this is what comes out of helioseismology. This is not my imagination or not a simulation. Our knowledge of the sun is skin deep, but it's amazing that we have these measurements at all. It takes an incredible amount of ingenuity to come up with flow patterns like that. And people have done that successfully. So we have a lot of information. And as you know, the sun rotates faster at the equator than it does at the poles, and all the things that you already know about. Now, given this magnetic field, what can we say? Well, it turns out that that induction equation that you saw, and I'm going to emphasize physics. I'm going to give you the equations so that you don't have to do pages of vector algebra on the board, but I'll just give you the answers. Nothing is very mysterious is going on. The magnetic field is represented this way. The velocity field is represented this way. And what you want are equations for B and A. Well, from the induction equation, you can write down the equations for B and A. And because of the symmetry direction, the big advantage is B has 3 components. But as I just showed you, if you know B and you know A, you know all the components of B. So that's the simplification you get when you write in terms of these functions, flux functions. And then this is del cross V cross B with rotation put in. BP is bipoloidal. And on the right-hand side, the red terms, which are the diffusion terms. And the rest is just vector algebra in spherical polar coordinates. Okay? The meridional flow is the independent advection of poloidal and toroidal field. So now if you look at this equation, notice something very interesting. There is no term involving A in the first equation. And if you come down to this one, you have A here, and this is a separate equation by itself. So differential rotation has BP in it, and there is diffusion. So this term is giving you a way to get toroidal field. So this is the picture that Dana was showing you, that imagine you started out with a purely poloidal field, okay? Purely poloidal field. And then you start rotating it toroidally through your omega, right? Remember the equation? Omega came in because of this toroidal rotation term. So you had a purely poloidal field and you start rotating it toroidally. Well, this tells you then how you can get a toroidal field out of it. A toroidal field out of the rotation. But what it doesn't tell you is how you will recreate from this without any feedback from the toroidal field that you created back to the poloidal field. Because this equation, the A equation, has no B in it. Do you see that? So what really ends up without the coupling between the two is that the diffusion becomes a sink for poloidal as well as toroidal field, and there is no term that is capable of maintaining the poloidal field against ohmic decay. Do you guys understand me on this? Now, this is a really, really important point. We were talking about how important it is to break symmetry to get the dynamo going. Now here you don't need to go to the computer. All that you've done is that you've built in axis symmetry. You've assumed that the magnetic field is axis symmetric and the velocity field is axis symmetric. And because of the sheared rotation, this term, you know how to use it to start with a purely poloidal field in the plane and twist it by the induction equation so that it develops a toroidal component. All of that is fine, but you have no way of getting the toroidal field feeding back on the poloidal field to hold it up. So in the meantime, if the poloidal field does go to zero by itself due to the decaying effect of resistive diffusion, the source that you need to create your toroidal field is gone in the first place. So you're dead on arrival. So with your differential rotation, as long as you have diffusion in the problem, as long as you have axis symmetry, you have no mechanism for holding up the magnetic field against ohmic decay. Okay, Cowling's antidynamo theorem, which I will state as a theorem, and because of loss of time, I won't spend a lot of time going over it, but the three bottom lines are important, but I won't dwell on it. Let me just quote to you theorem. Let me just say that if you look at the chapter 4, you will get a sense of how this theorem is actually proved. But this theorem was nothing more than generalizing the lesson that we just learned, that if you have a stationary axis symmetric magnetic field with currents limited to a finite volume in space, you cannot maintain it by a velocity field with finite amplitude as long as you insist on axis symmetry. So Cowling laid the rule down on what you needed to do to get to an understanding to what conditions you need to break in order for you to get a dynamo. Are you guys totally with me on why purely axisymmetric flows and a purely axisymmetric geometry will not allow you a solution of the large scale dynamo problem? And by the way, what applies to the sun is more general. It applies for any arbitrary system that you can come up with a dominant symmetry. And a very crude way of putting this is to say all dynamo problems are intrinsically three-dimensional. I am oversimplifying things a little when I say that, but one way to see it is what I just said. And I'll make this more precise on what kind of symmetry breaking you need a little later in the talk. But the history of this is that the fact that convection was key was known as early as 1919 by Larmor. Cowling's anti-dynamo theory was a bit of a killer because it was an anti-dynamo theorem. You have this, this, and this, you can't get a dynamo. So then the question was, how can I violate Cowling's theorem and create a dynamo? The problem just became harder. Well, 1955, Parker, as he often does through an intuitive leap of the imagination, pointed to a basic mechanism in which you could decompose the field in axisymmetric and non-axisymmetric parts, and by some sort of an averaging, which broke the symmetry, you could actually have a dynamo mechanism. And this beautiful physical picture was put in formal mathematical basis in 1964 by a number of people, but Brzezinski, Steenbeck, Krauss, and Radler. Radler is the only living person of Steenbeck and Krauss who wrote an EMF, and I met him a few years ago in Japan, came in from Potsdam to give, he's still working on dynamo theory, wonderful old-fashioned German physicist who does hundreds of pages of algebra still. What we tend to do using symbolic manipulator, he does it by hand. I have a separate story to share with you regarding Radler some other time. But Steenbeck, Krauss, and Radler was a graduate student then, developed the mathematical framework of what is known as mean field theory, on which I'll spend some time. And mean field theory turned out to be a great beginning, but not the end at all, because sophisticated MHD simulations taught us better and how to question the consequences of mean field theory and why we need to look beyond. And some of the questions are for you to solve in the future as you move forward. So what was this mean field theory? The mean field theory basically said, I'm going to posit that my system has turbulence in it. I will not at the present time stipulate what kind of turbulence it is, because part of my job would be to investigate how symmetry breaking has turbulence to be in order to be able to generate a mean magnetic field. So what we did was we went to the induction equation, and as you saw me go through it when I was defining the fast and slow dynamo, take the mean B, take the total B field and write it as a combination of a mean B field and a fluctuation, B prime, an average. And if you do that, you get this exact equation, our old equation, del B del T minus curl cross V cross B minus eta curl cross B. If you just average it, what you will find is you get del B bar del T curl cross, and you will get an additional beating term between the fluctuations, which in your average over is going to be non-zero. Mark this term. If it were not for this term, the averaged equation would look exactly like the induction equation. It just is the original B field is now replaced by mean B. The original V is replaced by the mean V. But now there is this term. And you can ask me, what happened to the term V prime average cross mean B, or B prime average got mean V? Well, when you average each of the fluctuating quantities, they go to zero, because that's random quantity by itself, each of them. But if you cross the two together, then that's no longer clear. The two fluctuations beating with each other would still give you a zero average. But what have you done? You have generated by small scale effects a turbulent electric field. It's called a dynamo field, which is the beating effect of the fluctuations V prime cross B prime, which now shows up in the problem. Now we don't know what this E actually is. Hopefully, theory will tell us how to calculate it, and that's what we are about to do, okay? But now, if you take this mean equation and you subtract it from the total equation without any averaging, this is the equation you get. This is not an averaged equation. It's actually an equation for the fluctuation B prime. Okay, now you look at this equation and you say, ah, nice equation. So if I can somehow solve for B prime, given a certain mean B field, if I can somehow solve for the fluctuating equation and plug in this equation, then I'll find an equation for the mean evolution of B and I'll have the dynamo problem solved. Except that when you do this exactly like I did, you have this funny sort of terms, V prime cross B prime minus the average. And if I'm to compute this term, then I have to go to further higher and higher level terms to calculate them mathematically. And you soon get into what is called the hierarchy problem in turbulence theory, that there is no systematic way to truncate it. So what people did in a first order smoothing approximation is to say, I am just going to drop this term. And this is what physicists do. When they can't deal with something, they just drop it and say, let me draw a simple problem first. At least if I can draw a simple problem, maybe then someday I can go back and deal with it. And so I'm just going to argue for the moment. I'll make the uncontrolled approximation that I'm just going to drop these two terms. So that's what is called solving the closure problem. And when you drop this term, you have the nice feature that you can actually solve this equation. Take my word for it that you can actually solve it. And Steenbeck, Krause, and Radler actually did that. I just wanted to share with you what the various steps and approximations are. And basically the assumption was that you have two scales, a very large scale L and a small scale LC. These for the fluctuations. And these are the longer time scales. This is the long time thing. So you're really looking at a multiple scale, multiple spatial scale, multiple time scale problem, where if you want to look at long-term variability, you're really talking about long time scales of tau L and long spatial range L. This is like the dimension of the sun. And imagine the turbulence is characterized by much smaller length scales and short-lived tau Cs. How does the mean field behave? And they did pages of algebra and they came to this solution that actually the turbulent EMF can be written in index form in this form. I want to quickly go to the vector form because that will be easier for you to grasp. And let me just go directly to the vector form because I want to save a little bit of time. What came out of kinematic theory was this, that, and I won't have much to say about a lot of other terms because you get a lot of terms in this multiple scale theory. The things that I'll focus on today are primarily the so-called alpha term that Dana was referring to you about. And why do I want to focus on alpha term? Because it has a very interesting structure that is unexpected. And the other term is beta times J. Now, beta times J is like the eta J term that you already know. So when Dana told you that turbulence can produce resistivity, he was right. In this limit, the kinematic EMF theory, or the kinematic dynamo theory, turbulence does produce a resistivity, but it does something else as well. And why is this a novel term? Suppose if you didn't do dynamo theory, right? I ask you, what is the ideal image to Ohm's law? You will say E plus V cross B equals 0. Okay? Because I'm dropping eta J for the moment. As I said, eta J is like my beta J term here. Let's say eta is 0. Well, what do you learn from E plus V cross B equals 0? What is E parallel in E plus V cross B equals 0? Somebody volunteer? What is E parallel?
V cross B.
Aha.
No.
Now, when I mean E parallel, I mean the component of E parallel to B. If you have E plus V cross B equals 0, I heard somebody say 0.
0, 0.
Yeah, see, if I ask you a question like that, the answer is usually 0 or 1. So 0 is the right answer. So ideal image tells you that E parallel is 0. But dynamo equation is telling you that the turbulence has the effect of creating an E parallel, which is indexed by this coefficient alpha, which we call the alpha effect, which is parallel to B. How can that be, you ask? And this is where the big point I made about how turbulence generates this E field out of the fluctuations is important. You modified the ideal MHD equations by bringing in a new turbulent generated dynamo field electromotive force, which has the property that there is in fact an alpha coefficient. And what do you need for the alpha coefficient to be non-zero? Is that the turbulence has the property, and I'm going through some equations because I want to focus on the concept, that the fluctuations V prime and the vorticity of the fluctuations curl cross V prime dot omega prime be non-zero. In other words, if you have simple two-dimensional flow or turbulence, imagine V lies on the plane, right? If you take the curl of V, what is omega? It's perpendicular to the plane, right? That omega dot V is going to be zero. So consistent with cowling, if things lie entirely on a two-dimensional plane, you're not going to get any dynamo, not going to get any alpha. But if you have an alpha, as I'll show you, you can actually amplify the mean magnetic field. But what kind of flows produces V prime dot omega prime? And it also adds turbulent resistivity, as we just discussed. That's your so-called term. That's going to always come along, but whatever it is can be overwhelmed if alpha is of the right size. And what is the alpha? And this is where Gene Parker's pictures became very, very important, which is that he pointed out that, in fact, if you have a stratification in the system, and the solar tachocline, if you think about it, the transition from the radiative zone to the convection zone is a highly stably stratified system. And when you do that and you have rotation, you have flows like that, which break the symmetry of the system and give you a non-vanishing V prime dot omega prime, which has come to be regarded in turbulence theory as the kinetic helicity. So flows with non-zero kinetic helicity. And if you have non-zero kinetic helicity, you are breaking mirror symmetry. Gives you a non-vanishing alpha effect. So something very important came out of kinematic dynamo theory. It came out that if you have turbulence in the system, and if the turbulence has finite kinetic helicity, another way of putting it is to say V prime dot omega prime is non-zero, which breaks mirror symmetry, as shown in this cartoon below. Then you have an alpha effect. And if you have an alpha effect, how does it change the picture? Like when I went ahead and wrote down the so-called picture where we bemoan the loss of any term in A that brings us B into the problem and helps us solve the dynamo problem for the sun, guess what happens? As soon as you put that alpha B term in there, now A is coupled to B through this equation, which would be zero if the dynamo effect is zero. And then you know you're in trouble because your A will decay away and there is nothing in B that bootstraps that A. But now you, with differential rotation, you started out with a magnetic field which is poloidal. You created a B, and then the B goes in strength and then enters the A equation. And you could imagine a situation for particular values of alpha where B will hold up A and A will hold up B. And you have a dimensionless measure of the strength of omega and alpha. And this is where what Dana said about the dynamo number becomes important. It is a product of this d omega and d alpha. Note that they're dependent on these quantities. Okay, but it does include a coefficient called alpha, which has now been computed purely out of induction. If alpha is zero, you're in trouble and the dynamo number is zero. But you really have to have the dynamo number exceed a certain value of D critical. And when you do so, this equation has steady state solutions that are sustainable. So therefore, the entire dynamo problem boiled down to, do we know an alpha for the solar dynamo? But so was the problem for other areas. And all that you have to do is to make sure that alpha was large enough to beat the effect of resistive diffusion. And that became the ball game of dynamo theory. As Gene Parker, who I deeply admire, once made a joke. He was one of the progenitors of it, but he knew what the computers were teaching us. And I remember him making the joke, why should we be so satisfied that if you have two parameters in a problem, that you have solved the problem? Because he claimed you can fit the Manhattan skyline with 2 or 3 parameters. So you can map out the universe's magnetic fields by just assuming that these coefficients are somehow working in your favor. But are they really working in your favor? Well, if you think you know those numbers, the answer is yes. And so what happened was people wrote dynamo codes, and they were very happy with what they understood to be the solar dynamo working. And lots of codes like this exist, and they give you very convincing pictures. I'm a skeptic. I'm a skeptic because I like to think that what kinematic dynamo theory has taught us can really be held up if we go to the question of when the magnetic field becomes stronger. And if the magnetic field becomes stronger, that induction equation by itself cannot be taken isolated from the rest of MHD, because what the induction equation assumes is that you give me a V and I'll tell you the B. But if the B grows in magnitude, it's going to go back and affect V and change the view you gave it. And how does that back reaction affect the growth of the magnetic field? Well, it's not easy to do that problem, because you have to deal with the so-called feedback problem, because as you know, the momentum equation has the Lorentz force term, J cross B. So if I may take you back to the very first set of equations when I start out with Rempel doing all this calculation, what I'm referring to is the fact that we were focusing on this guy alone. And now I come back and tell you, wait a minute, you prescribed the V and B is growing and you're going along. So far you think, well, and alpha is rescuing you. But what when the B changes the V through this equation, and that V will then come back and haunt you? That's the self-consistent problem. I was not the guy who asked that question. The people who were doing MHD simulations asked that question, and what did they find? Well, what they found was that these effects are very important. And in a pioneering paper, Ohmic Decay, she tells me, and she is a well-known turbulence theorist, by the way, but this is one of her early papers. And she tells me this is the best paper she ever wrote, written with Uriel Frisch and others. And what she pointed out in this paper is that there is a back reaction that occurs, that the alpha effect is modified. You saw omega prime dot V prime is there, but there's a term that comes in, which is J prime dot B prime, which is what is called the back reaction term, that'll become larger and larger as the system evolves in time. And this term has the effect of diminishing alpha. And this then would tend to minimize alpha. The effect was already there in Decay, and it was arrived at analytically. And she actually got that effect by not only considering the induction equation, but bringing the first important corrections from the momentum equation into the problem. And she made approximations too, but she analytically arrived at this formula, which was a precursor of things to come when simulations got more well-defined. And what really happened was that unfortunate news was that when you start out in a fully MHD simulation, what happens is that the smallest scales grow most rapidly. And due to the constraints of magnetic helicity conservation, the small scale fields then act to decrease the large scale growth drastically, which was called the problem of catastrophic quenching by Grizinov and Diamond by Catania and Hughes. These are people in Chicago and United Kingdom. And there were people who got up and they said, well, yes, maybe you have quenching, but you guys are not doing the problem quite right, because if you do the problem with periodic boundary conditions, with not having an open boundary, you're leaving out an important mechanism by which helicity can be injected into the system. I won't bore you with all of that. I contributed to some of that myself with colleagues, but there was no question at the end of the day that the back reaction on the problem was very, very hurtful to the cause of dynamo theory. And the fact of the matter is that even moderate Rm, the fast-growing small-scale dynamo, implies that velocity fluctuations should always be accompanied by magnetic fluctuations of similar magnitude. And therefore, there is no limit really at which point you can kind of say, this is the regime when I know kinematic theory works, except at the very, very early instance. So therefore, in my opinion, unless you really back it up with a lot of work, computational and analytical, you should view with some skepticism predictions that are made that are purely reliant on the induction kinematic dynamo model by itself.
So Amitava, before going on, there's a little, there's a question here. Someone wanted to see you explain the little loop picture that shows the rising and falling plumes breaking the symmetry, essentially.
Okay.
How that breaks the symmetry.
Okay, so thank you for that question. So you see the rotation direction and the stratification direction. This is really a slab-like picture of how there is overall background picture of the stratification and the rotation. And what you have here are the effects of stratification drawn better. These are the green and the red arrows that I'm showing. And the kind of rotation that gives you this effect breaks the symmetry. Do you see that? Is anti-clockwise, if you will, depending on whether you are seeing it from downwards or upwards. That breaks the symmetry. So does it here.
Yeah, got it.
Stratification, this is what breaking the symmetry.
Okay, I think that answered the question, right?
Okay. All right. So now let me go.
And you have about 15 minutes.
Oh, great.
Or no, 10 minutes maybe. Hold
Okay.
on.
Okay. Well, I think I need about 10. I know I speeded up a little and didn't dwell on the algebra because you know what? I think you're entitled to the facts. The algebra is partially discussed in chapter 4, but the physical picture is far more important than the algebra. There were good mathematicians doing their job and they did it well. And so there is nothing wrong once you give them their equations and their assumptions of the scale separation, the thing comes out. And when I teach this at my graduate course here, I always focus on the physics and I leave it as a homework assignment with the adequate reference for my students to go out and derive the alpha effect after about 5 to 6 pages of algebra. And that's important algebra to do. And I hope someday all of you do it if you haven't already. But if I take too much of your time going over that, it won't be as instructive as you doing it. What I want to talk about today is that you might say, well, you're leaving us with a very, very pessimistic picture of the dynamo. What you're really saying is, as soon as you have back reaction, you have this tendency to suppress alpha. But is there a way out of this? Because we do know that large-scale dynamo magnetic fields exist. So the basic dynamo picture must be right. And you guys are all screwed up running on these complicated simulations, and simulations are so complicated and you can't get the facts out. You need to work harder at it. But we really do have the dynamo, whether you understand it or not. So nature in that sense is calming, makes us feel stupid that we haven't figured it out. But it is true that the kinematic dynamo theory did give us an alpha effect. And the problem is that we don't know how to keep that alpha effect going because we are saying turbulent fluctuations completely kill us. So I'm going to present to you a possible solution to this problem, but I must forewarn you that this is something that I'm very biased about, but take it as one possible answer, and there may be others that are even better. And this actually came about from studying that I had the privilege to work with a very talented student, Jonathan Squire, and this dynamo problem that we are dealing with that we just discussed, namely that you do have strong magnetic fields and you do need a dynamo, is as much a problem for the accretion disk as it is for some planets, including planet Earth. The accretion disk is the disk around a black hole that many of you know forms, and it has magnetic fields. And you know what it is? What is amazing is that the large scale magnetic fields in accretion disks can actually be simulated. And the simulations are done. We do not have direct measurements. We know even less about the accretion disk than we know about the sun. So we rely even more on simulations. And one of the things that happened in accretion disk theory that you may have heard about is called the magnetorotational instability that was first discovered by Chandrasekhar and Velikov, but also independently by Balbus and Hawley. And Balbus and Hawley pushed that instability to suggest that it could be a possible mechanism for the understanding of large-scale magnetic fields on the accretion disk. Now, here actually the job is made just a little easier in the following sense, that people who are doing fully compressible MHD simulations, which were unstable to the magnetorotational instability, actually saw large-scale magnetic fields come out of their simulations. Now, it had all the limitations of simulations. Now, these are first principles. Now I'm talking about Matthias's Rempel's MHD equations. You're integrating them full scale on large-scale computers, and guess what? They're beginning to see large-scale magnetic field emerge. So you can no longer say then, and the way they did it is that first they did a global domain, like I'm showing you. Here is your black hole, here is your accretion disk, and you translate that to a stratified shearing box. You take a box and you blow it up and you set up the right boundary conditions. This is what it's called, the stratified shearing box. And then you even go to the unstratified shearing box where you have completely got rid of all gradients, and you're doing the really simple physics problem. So in the first step, you got rid of curvature, and in the second base, you got back to all stratification. Guess what we learned out of these simulations? Turbulence produces large-scale magnetic fields. Aha! So then this becomes then a problem of theorists now. Even the simulations applied to this case is showing large-scale magnetic field growth, and so it's very promising. You can no longer say this is a kinematic study because it's a fully self-consistent study. And what did they mean by that? If you look at, and this now I'm showing you results from Squire's thesis, Jonathan Squire's thesis, that you take a box in which you impose a certain mean magnetic field of this kind, and you put in a sheared flow that is unstable to the magnetorotational instability, and you're imposing boundary conditions which mimic what is going on in these large-scale simulations, and you let this run. And guess what? You see large-scale dynamo field evolve with finite alpha coefficients that are, or seemingly finite alpha coefficients. Well, what was interesting was that Jono investigated this further, and what he came to the conclusion was that he was actually getting this large-scale dynamo to grow without even having an alpha. It is as if that dynamo equation that we wrote down was itself incomplete. And in fact, what he noticed was that when he imposed flows where there was no alpha, beta became a tensor, the beta dot j term, and there were off-diagonal terms in that which actually produced the dynamo effect. And what was really important was an important physical effect, is that, by the way, he was my student, as I mentioned to you, and for his discovery of this effect, he got the Marshall Rosenbluth Dissertation Prize in 2017 for APS, and I'm very proud of him, so I like to show his picture. He's right now a professor at New Zealand, which is where he came from, and he has his own group today. But the really important thing that he made a point about was this, that, we think of the small scale dynamo as really bad for you. It overwhelms the mean field growth. But his discovery was that if you look at the energy spectrum and watch it as a function of time, what happens is that the thing just grows in the beginning and you get a lot of turbulent growth until you hit the saturation. And then if you look at the energy of the magnetic field, this is what is happening to the magnetic energy of the fluctuations. And if you look at the energy, what you find is that after the small scale dynamo has saturated, it begins to drive large scale growth in the system. And the large scale magnetic field grows after the small scale magnetic field fluctuations, the kinematic dynamo or the fluctuation dynamo has already saturated. He called this the magnetic shear current effect, and this showed up in his simulations, and he has written about 8 papers on this subject that I urge you to look at if you ever had interest in this problem. But the dominant thing of it was that you needed sheared rotation. And when you did that, the large scale dynamo didn't show up while the small scale fluctuations were rising, but you waited long enough in the presence of Keplerian flows, and they would actually reappear in your system on a large scale. Admittedly, the RM values for which he ran the simulations were not very large. And so the question remains, is this mechanism valid at the Reynolds number of the accretion disk? Unsettled questions, no simulation can be run at the present time. And why these are challenging simulations? Because you must resolve the simulations, both the small scale and the large scales at the same time. What may be happening, is there any evidence that this could be happening in the sun? And I want to cite a beautiful study by Hotta, Rempel, and Yokoyama that was published in a science paper. And they did not know about Squire's work on the fluctuation dynamo, driving the large scale dynamo over long time scales, but they made, this was one of these heroic computer simulations. And I talked to Matthias after the fact because the papers appeared at about the same time. And we didn't know about Rempel and they didn't know about us. But what Rempel made, as Hotta, Rempel, and Yokoyama made the point that if you want to capture the solar dynamo, and it's not clear that the magnetic shear current effect is what is doing this, a lot more work needs to be done before we can say that. But let me just say what the lesson of this simulation was. The lesson of this simulation was that if you want to see large-scale magnetic field growth from first principles in the sun, you must run simulations that will resolve your small as well as large scale simultaneously. If you gloss over the small scales and thus take their effect in as some kind of an alpha effect, you're not doing justice to what the small scale physics actually is. But if you have to resolve both scales, then you're really looking at hero simulations and powerful computers which have the ability to resolve both types of scales. And as you know, the United States is going to have its first exascale computer later this year, and 2 of them by early 2022. And this is an exascale problem, which I hope will produce even better results. But let me leave you with that, with some unanswered questions and some perhaps tantalizing possibilities and where an answer may lie, but by no means the only one. And I don't mean to suggest that the Squire mechanism is universally accepted. It is not. There are people in the solar physics community with whom we are running discussions, if not disputes. So think of this as a wide area of work that I hope some of you will get involved in someday. Thank you for your attention. I'll be glad to take questions.
Thank you, Amitava, right on time, 1:15.
Thank you. Thank you for moderating, Dana.